Hello, everybody. We'll get started in just a couple of minutes.
Okay. Can people online hear me? Yes, fantastic. Okay. So the reason we came up with this workshop was because, as I said, I'm very excited about this whole idea of routers or routers, however you want to pronounce them, going at huge speeds in space. They're not exactly routers at the moment, but they could be routers. So it's a new kind of internet architectures. And what we wanted to do was explore, what I wanted to do personally was to explore how this would work. But I found that I actually didn't have half the knowledge I needed. And we conveniently have Professor John Black, who wanted to do his sabbatical here this year. And he's an aerospace engineer and literally does rocket science. So we needed rocket science, not just networking stuff. So it was a very good combination. And what we've been doing for the past year is to sort of do some initial measurements, work on it, build a test bed that's scalable. And it seemed like there was a community out there that of computer scientists doing stuff related to this, many of whom are actually here in this room now, and some will be joining us online talking about it. And we wanted to get the perspective of this community, the networking community, as well as the aerospace community, and see what the new research questions are that we might want to focus on. And it's not just the Starlink-like networks or the UK's OneWeb-like networks that we are interested in. We will also have some talks about the cislunar architecture and the LunaNet architecture that NASA is coming up with for networks around the moon. So in a few years from now, when the Earth is a wasteland and we are all on Mars or Moon, that's the kind of architecture you'd probably be needing. So this is truly blue sky thinking research. And I guess the other final thing that we also have at the end of this workshop is to have a bunch of funding agencies and come and talk to us about what the opportunities are and what their interests are in this space. And so we'll have a two-way discussion, hopefully. And we're trying to get this done both as a online as well as a hybrid workshop. There's a huge amount of interest, actually. We had to close registration, unfortunately, a couple of days before the workshop. So we are actually doing a live stream now as well. So if you couldn't register, or if you have colleagues who couldn't register, they can use the live stream to join in. So with that, John, I don't know if you wanted to say anything more, or should we go for the first talk? Yeah.
Thanks, Nishant. No, I just wanted to say quickly, thank you to Nishant and Mohammed and the computer science department for having me and for working with our team remotely at Virginia Tech. So thank you guys also at Virginia Tech for being there and dialing in here, and for all of our hard work over the last year. And thanks again, everybody, for being here. So what we're going to do is connect up and push the slides over Zoom. Audio is okay for everybody online, right? Yeah, good. Okay. Okay, great. Our first speaker is Gory Fairhurst, and he's an internet engineer, has a chair at the School of Engineering at the University of Aberdeen in Scotland, and has built from initial work on the internet over satellites since 1999, and has developed a focus in what he is calling internet engineering. So I won't take up too much time, but thank you for being here. And I will,
let's see if I can hold this. Yeah.
Hold it, or it's a metal thing.
Okay. Well, if people can hear me, I assume you can hear me unless you tell me otherwise. So I'm going to talk about internet standards for next generation of satellite systems. I'm unashamedly not going to talk about LEOs particularly. I'm going to talk about satellites, and I'm really going to talk about internet engineering. But I hope that these are really important things before we get to talk about the other things, which is kind of like building all this system that's going to support these internet applications. So, see if I can advance the slide. That'll be good. Okay, so 40 years ago, when I started out on this story, one of the important things I realized was you have to speak to lots of different people to be able to build a successful satellite communication system. You really do need to talk to people who know about dBs and hertz. And you really need to talk about people who are using applications on their phone or their computers. All of these things are equally important in getting the solution you need. 40 years ago, we built systems particularly for a particular application. All the research was devoted to a particular project, a particular customer. That's clearly changed. Systems were universally expensive. Jessica's holding a tiny satellite terminal from the 1980s. Yes, they existed. Yes, they were incredibly expensive. Now they're common price. This was a 2-meter petrol antenna. You could assemble this in 30 minutes if you were smart and get the link going. And all these technologies had a packet component. So packet over satellite is not something new. However, now we are working with systems which are over 1,000 times faster. I'll not try and estimate how much cheaper they are. I gather from people in the industry that we're aiming for £100 for a satellite terminal. Well, okay, that's our goal. Mass production may well get us there. All these systems are broadband. That means they all have an internet protocol stack running over them. And in the future, yeah, we will have a combination of LEO, MEO, GEO systems out there. Which ones are the most dominant? Well, I guess the market will determine. But all of these systems will be internet-based, and some of them will become major suppliers of communications infrastructure in the not-too-distant future. So, what do we need to know from the internet point of view? Well, in the original look at this 40 years ago, all we talked about was throughput. Now what we talk about is latency, the time to move objects end-to-end across the internet path. Latency is a good metric. And the problem is the satellite portion that we add when we put a satellite system on that path has different properties to fiber and copper. It has some propagation delay. It might be fixed, it might be variable. We might have to compensate in some way with buffering. It maybe has handover impact. There are probably other design considerations that come because this is a radio-based technology. So we're always going to be trading power, frequency, buffering, etc., against one another to build the system and to operate it efficiently. Until very recently, all these optimizations were inside the satellite equipment. And that's the first thing that will change as we look forward from now, because you can't do that anymore. When we had the optimizations inside the satellite equipment, we were using the TCP protocol, that well-trusted, loved protocol, which we used with the web for decades. We invented something called PEPs. And I'm going to show a few graphs with performance. These graphs show on the vertical axis download time in seconds, the latency, and then a sequence of bars for different network protocol stacks. On the right, we have here, if you can't see in the room, this red line indicates a set of experiments done in a recent ESA project to evaluate TCP over the latest broadband satellite systems. And they used a VPN. The VPN encrypted the traffic so you couldn't enhance it in the satellite system. What we were really doing was looking to see how good these protocols were as supplied by Apple or Microsoft. You know, how good does it work just out of the box? And you can see here that to download this particular object, this one web object, took between 6 and 16 seconds. Why the variation? Well, because different platforms had actually customized their stacks in different ways, and different web servers had offered their service using different options. If you use the latest Apple stack, you got performance on the good side, the latest Microsoft stack also. So things are good and improving. But our satellite systems currently include PEPs, the Protocol Enhancement Module, and their performance is still better than even the best protocol stacks. The green bar shows the performance of a TCP PEP, in this case, the IPOS PEP from Hughes, and you can see the performance is like 4 seconds to download this object. That's a second or so longer than it takes on my DSL link at home. It's not too noticeable, it's pretty good. But then in 2021, we had Quick. Quick is probably the technology you will use if you're using a Google service or you're using the internet. We've moved on from using TCP to an encrypted transport protocol. With Quick, all you see is the initial handshake. The first 2 or maybe 6 packets going backwards and forwards, and the rest of the data is fully encrypted. You can't do any enhancement in the satellite system. That marks the end of PEP. So what do we do? Well, one of the things we did was we approached ESA and asked the European Space Agency for funding to say, how well will Quick work? Is it possible to influence Quick back over in the years before 2021? Could we influence it enough so that the standards actually reflected something that would be reasonable for a satellite use case? So here's data evaluating the Quick specification as it emerged. You can see the 2 blue bars here. They represent Quick on the left, using just Quick, and on the right, using Quick over a VPN encrypted tunnel. And I assert that really Quick is not that different to TCP. The basic design of the protocol in the first take that's now being widely implemented is actually reasonably similar to TCP's performance after 40 years or so of evolution. That's a pretty good starting point. It's not the same as we had when TCP started, and it worked rubbish over satellite. So this performance is probably okay. Can we do better? Well, we can do better, but before we go and look at that, we should realize that when you do Quick over a VPN, its performance is the same. Now, there's an interesting fact because people are starting using VPNs, and if you operate a satellite system, you probably saw a massive change in your traffic in the past 2 years as most of the customers moved over to VPN services, and their PEPs again became ineffective. So VPN traffic is important, makes no odds for Quick because it was already encrypted, so you rely totally on what's implemented in the end systems. If you wanted to get better than current Quick, you could do so by changing the design of the Quick protocol. And there are proposals to do this. The basic limitation from using a geo satellite link, this is geo data, is that the performance could go down to this line here. This represents 9 round trip times of transfer to move the data across the network, which is the maximum allowed if you use TCP's style of congestion control. But the PEP does better than this because the PEP realizes that the satellite resource is actually available and you can basically tune to use all the satellite resources available. So you can move down to this green line. The difference between these two, well, you might reach that if you could persuade Google, if you could persuade other content providers to change the way they use Quick. And here's the good news. At least at the Internet Engineering Task Force, where they do the Internet Transport Standards, people are listening to ideas to change that. And if Google decides to change it, if Cloudflare decides to change it, they can make that change within a month or so. The evolution of the end systems can be much faster than it could ever have been with trying to evolve the satellite equipment. So I think for performance, there's a good story here. We have, as a satellite community, influenced the standards And they've actually built something which not only works reasonably well, but which we can continue to evolve. But this is all about performance. There is something else in the story that also is important. What do the users think? Well, how is this user experience when you use a satellite system? How bad was it originally? Well, the answer is it might take you 3 minutes to download a web page, particularly if you handcraft the web page to be difficult to download. So here's a classic handcrafted web page. It sends 243 small icons of flags all on the same web page and tries to do it as fast as possible. This test was designed to highlight how good the new web protocols were. So you can believe it or not, because any test depends on how you target the test, what you actually look for. This test, though, with the original HTTP specification, took a little while to download things. You see each flag appearing one at a time. In fact, to download the entire test sequence took 30 seconds using the original HTTP spec. This was actually with protocol enhancement in our satellite terminal. Now, 2015, everything changed for the first time with the introduction of HTTP2. And using HTTP2 on the PEP, you can see the download. These are real screen captures from actually doing the test live, and they are utterly representative of the data set. How good is HTTP3 if you actually use this test? And the answer is pretty good, about 11 seconds. Whether it's 11, 10, or 9, kind of depends very much on which server you go to, rather than anything else. But really, even if you look at this level, things are looking reasonably good with this test. And to give you an example, how long did it take over my home DSL link? Well, it took actually between 5 and 10 seconds. Well, that's a 24 megabit DSL link over copper. Well, performance looks like we might be in a place where we can actually influence the standards and where the current technology might work. What about system resource usage? Is this a service that can actually be sold for a satellite system? Here we get into a more tricky position because we get into a story that is also common for other radio technologies. And this applies not just to GEO, where my first part was focused on, but also to MEO and LEO systems. All of these systems care about bandwidth and power in combination. And the thing that has happened over those 40 years is the number of acknowledgements has significantly increased. As the rate increased, so also has the rate of acknowledgements. If you have a 250 megabit per second satellite service, over 10 megabits per second of capacity is being consumed simply by the protocol sending acknowledgements back on the return link. If you're a radio engineer, you maybe fear this a little bit because this return link is often shared and becomes a very expensive resource. It's more costly than the forward resource. So can we reduce the traffic on the return link? Well, why don't we worry about this? Well, the answer was because the PEPs that we use for enhancing performance also optimize TCP return traffic. So this wasn't a problem until a couple of years ago. But it now is something we might want to worry about. And quick packets are actually much bigger. Quick mimics TCP in its pattern of acknowledgements, but it sends bigger packets, 50% or more bigger, and current developments in the IETF are suggesting adding ECN support, timestamps, other things that might make these packets still larger. So it's kind of something that really needs to be thought about. Different quick implementers have made different decisions, but all of them are larger. The IETF is currently working on a method to reduce the amount of acknowledgement traffic. This turns out to be a huge problem in a data center also. Thousands and thousands of packets being sent simply to say, I got a byte. It's crazy. the IETF is working on it, and hopefully new standards will emerge in this space in the next year or two. And these standards will be something that can be deployed to help address the return link resource consumption. Watch out for that. That's currently in standardization. Once standardized, it will have to be implemented. And the curious thing for any satellite system that wants to try and take advantage of it is you will have to speak to your content provider and probably the web browser community to get this implemented. This does not touch your satellite system. What I'm heading for and trying to motivate is that as we think about the next generation of satellite systems, we have to understand their performance and their trade-offs, but the people who have to take up and change things are actually not satellite systems engineers. From the internet perspective, they are the content providers, the operating system developers, the web browser manufacturers. They are a different community, and we have to build links with these people and involve them in a way which stimulates them to implement the things we might want to see. Fortunately, I believe they will listen. I can't finish my talk without suggesting that this is not the end of the story. I talked a little bit about forward performance or the time to download objects. I talked a little bit about the amount of resource consumed on the return link. We also need to seriously think about buffering in our systems. Satellite systems typically transmit their data using some radio resource allocation method. They always buffer data. How much data? We have to decide. How they handle that buffering, we have to decide. Again, this is not a new topic. If you were to delve into any bit of satellite equipment that does an internet service, you would find it supports some form of prioritization for its buffering, and it's configurable. However, the current systems all rely upon reading the packet headers to decide which packets go into which queues and how to configure that buffering. They work smartly, except it's no longer smart because with encryption, you can't just look at packets and decide what they are. You have to have some other form of signaling or some other heuristics. So in a recent study we did with ESA help, we looked at using machine learning methods to try and figure out what types of traffic was flowing across the network. It turns out simple heuristics might actually help you a lot in separating different types of activity. Maybe we could have used some sort of code points. Maybe we could have used active AQM methods, active queue management. Maybe there needs to be even more interaction. Perhaps there are opportunities here for talking to satellite routing and saying, this is a phone call. You know, it's got low latency. This is a bulk data transfer. Well, it just needs lots of capacity. Maybe these things are useful. Maybe if you're doing things like multipathing in a transport, maybe this is interesting hints to tell you how you wish to use the service and how the satellite service should provide it. There's many different things might go on, but buffering is probably going to be one of the key things we need to look at next as we do this work. So what are the implications if you're building a satellite system? What have we learned from all this experience? Well, the first thing is be ready for encrypted traffic. Everything's going to be encrypted from now on. People care about performance, people care about cost, but users care about privacy. With privacy and encryption, you have to expect that you can't delve into packets, which means that satellite operators no longer control the protocol trade-offs, although they really want them to happen. How do we make this happen? Let's hope we can say that we can influence the standards community. I think they will listen. So I'm motivating that we should all talk together and we should approach the standards community. Let's talk to the Internet Engineering Task Force and tell them what we expect to have in a satellite system-friendly version of the internet. Let's talk to other people. Some of the problems we've had in satellite have been that satellite terminals are expensive. Well, that's because we don't have common standards for the actual equipment, at least not in the same way as mobile people do. If we have many of these, we have opportunities for economies of scale. There's a wonderful opportunity for standards with equipment. There are opportunities for standards for the internet part, And there is a growing expectation that the satellite network as a whole is actually something that's managed and integrated with the terrestrial infrastructure. There are a number of different people trying to build the northbound interface for a satellite system. That interface that lets you talk to the satellite network and tell it about different routes, about capacity requirements, about costs. So I'm saying that standards is something that's going to be important to change as we move ahead. And that was really the bottom line of what I wanted to say right now. Let's see if anyone's got any questions. What I think will be really helpful as we go ahead is to listen to each other. There are many different people in the room with many different aspects of their involvement, and it'd be really good just to chat as we go along through the couple of days. Okay. Anybody, any questions or observations they'd like to make?
Hi, Corey. Thank you very much for the talk. Very interesting. And concerning standard, you know, in the IETF, they obviously doing the standard, and also HC and IEEE recently, they also look into the working group on satellite, and also ITU in general. And do you see where they will be able to collaborate in somehow to get into everybody into the same direction and to work together? Everybody, you know, as before, they just continue to do their own standards. Yeah, that's a general question.
Okay, and the answer I think is easy. No, they will continue to do their own standards.
Okay.
However, what is really important is that each of them knows what they're actually doing and tells the others what they are doing. There are more groups as well. There are a number of groups working very much behind the scenes to do the network management piece here and to do that northbound interface. So there are groups doing different things. At the moment, I think what we have is a problem because the other groups do not know what they are doing. So what the ITU does is not immediately visible to, say, the IETF. What ETS is doing is not necessarily visible to someone else. And this is because we're at the start of standardization. And we really need to make sure that all these different pieces work together, I think.
Concerning the northbound interface, are you reference to the software-defined network, or that's kind of a, you know, scenario of?
Software-defined networking is definitely a component of this northbound interface. Yeah, modular components build services, modular components to manage the service. There could be software-defined networking. There are other things also in this space.
Great, thank you very much. I will talk to you later, Corey.
Okay.
Corey, this is John Border.
Hi, John. Nice to hear from you.
You didn't bring up the topic of packet loss. Clearly, that's more of a problem for GEO than MEO and LEO, I think, because it's latency related. But one question I have, and maybe you might not know the answer, but do you think packet loss is going to be an issue with respect to lots of handoffs? Because particularly when you hand off a gateway, because all of a sudden packets got to be retransmitted from a different path. Is that going to be a problem so that even the lack, you know, one of the things PEPs do for you is recover from packet loss locally, and we won't have that anymore. Maybe I didn't phrase that well enough, but hopefully you got the gist of what I'm asking.
Okay, so I'll not stand in front of the speaker. John was asking, John Border has been involved in many parts of the story, and he was asking, what about packet loss? Are our services actually lossless or not? Now, when we set out on this story, they were definitely lossy. Since then, we have definitely got better coding and adaptive systems that can make them rather unlossy, fairly reliable, in fact. However, there are two parts to this story that make packet loss actually quite important. So John's got a really good point. The first one is not all services are actually to a satellite customer. If you're delivering to a satellite handset, then that's the endpoint. And that might be a service you can actually build very robustly. But if you're delivering onwards on a Wi-Fi link, then that Wi-Fi link that's part of the end-to-end path can actually be quite lossy and unimportant, except when you couple it with a satellite component for the delivery path. So loss is probably going to be something we have to solve. Then, of course, there's the question when you've got handovers and LEOs and satellites where you can take options and going one way or the other, and then loss becomes again infused into the whole idea. And you can solve loss by buffering. We don't want to do buffering, so we have to solve loss by a smarter method. Yeah, loss is important, John, and I don't have a solution.
I'm going to ask a question which has been asked on Zoom by Guoliang Shui about what's the communication range of geosatellites and what about the communication range of LEO satellites? A clarification question.
I missed the question. Sorry.
What's the communication range of geosatellites and the communication range of LEO? I guess how wide do each of them cover?
Okay, right. So I mean, so a typical geosystem will reach all satellite terminals within its footprint for the beam that you're using, which used to be sort of 1/3 of the Earth's coverage, and typically now is much, much smaller using spot beams. But generally, geosystems have been designed to cover very large areas. LEO systems, on the other hand, have lots of little beams that are typically moving at very high speed. You put those together, you build a carpet, so you should provide also global coverage if you have a full constellation. That turns out to be a lot more tricky because if you only had a few customers, that would be very easy. But then when you put all your customers into a certain country and other countries where you don't have customers, then you have to somehow work out how you're going to provide the capacity to the people who need it in the place where they need it. Yep. So it's not a question I can just answer. It's a question that has to be asked to a service provider when they actually build their system.
Thanks. I'll ask one more question from Zoom, which is, I guess, quick and TCP, etc., end-to-end protocol. So whatever they do is affected by all the intermediate links, of which satellite would be just one component. Are there examples of optimizations for satellites that would make other link types worse or vice versa?
Yes, I guess we can always find some optimizations which will make some things worse. One of them could be go back to John Boyder's question, how do we deal with packet loss? If we have a satellite path that loses perhaps one packet in 1,000, but it does so often, every 1,000 you might lose one, obviously one could simply add forward error correction to your service end-to-end across the internet, increase the bandwidth used, and you'd fix the satellite service. For other users, they might think, why are you sending more packets than you need? This reduces our performance. So trade-offs, yes. Significant trade-offs, I don't know of any really significant trade-offs. The question is, will the system be adaptive to the type of network that's being used? And will the content operators be willing to jump on board and help us? Because we're really talking now about Cloudflare, Fastly, Quick with Google, etc. These are not normal players to engage. And it appears at the moment they are interested in helping.
So from our experience, it looks like Starlink, for example, terminates in Google Cloud Centers. So, part of the question is moot if it always terminates in a Google Cloud Center, I guess. Yeah,
but who's serving the data? Is Google serving the data, or are the Google Cloud Center simply bringing the data from somewhere else? This is a whole system, and we have to be ready to design an internet service that's internet-wide, not just a link.
For the big players, yeah.
The capabilities of different types of satellites varies a wide ranges, going from GEO all the way to CubeSat. Very, very different. So the solutions may also probably be different depending on the capabilities of each of the satellites.
Yeah. And one thing I can tell you from all my years of experience is if you try and tell Apple they're going to produce a different solution for each of your different communications network, they're not going to listen to you. So we need to build something that is common for these different systems. And this is at the application and transport level. The technologies underneath will be vastly different. But the question is there a possibility that we can build something that we can just expect to use from our MacBook, from our phone? And if you have to run a special app to use it, well, good luck, but you're not going to be providing an internet service.
If it's a small satellite, then whether it will have the resources to process all these things in a reasonable amount of time, that itself is a question.
Yeah, and it won't probably be part of the internet. You never know, things can change. I mean, we have the whole IoT subject. Whatever is IoT or whatever the solution is there, maybe that's applicable to some of these. There's DTN, people have talked about this. So there are a number of technologies out there, but the internet technology as a whole probably has to be something that operates at the sort of bit rates we talked about, which is providing a service that you can just use from your end system.
And the other thing is that the LEO satellites are also not really new. So for example, Iridium was built 25 years ago. LEO constellations.
Yes.
LEO constellations and Iridium didn't quite work out, probably because of commercial reasons, not so far as the technological reasons.
And indeed, there were other satellite systems before that, which were very well developed, but never met the light of day. And also big geo systems, which did clever things on board that never reached the light of day. So yeah, this is not just technology, it's about markets.
Yes, yes.
You have to get people to buy your equipment and service to be able to get their money to build the system that you're trying to sell them.
Right.
Good fun, eh?
Last question.
Oh, yes.
So as LEO satellites come online and we start to see an awful lot more variable paths in terms of latency, and potentially as the ISLs come online, a lot more multipath, do you think it's finally time to fix our transport protocols to cope with reordering gracefully?
Yes. Because this is a very good case of where we can actually start to change things that other people will think is a good thing to do. And I think there's an opportunity there to get to the people like the IETF and put things forward, which Google will just say, yeah, we actually have a similar problem in our data centers. We actually have different ways through our data centers that go out across countries, because in Google's thing, they don't just build a data center, they connect it via this hidden infrastructure to another data center, so they become coupled and they have different paths that take quite a while. I think you'll find people who will happily talk about different paths with different properties, and the satellite system may not be that different if we put it in the right context. I think this is a really hot topic. Yeah, we should definitely be looking at that one. Hello.
Mine doesn't seem to be working. Probably borrow yours.
Sure.
So the next speaker we have is Devopam, who recently joined Microsoft Research in Bangalore as a senior researcher. He did his PhD at ETH Zurich on new space satellite networks, and he's got so many awards in his PhD and in his short career so far. The IRTF Applied Networking Research Prize, a Best Paper Award at IMC, and a Best Dataset Award at PAM 2020. And his work on speed of light ISPs was published at NSDI this year. So you can talk to him about it if you get the chance.
All right, I hope I'm audible. So hello, everyone. Welcome to my talk on understanding and evaluating the performance of low Earth orbit or LEO satellite networks. So in this talk, I'll first touch upon the LEO hype, the technology enablers, and broad opportunities. We'll then briefly dive into LEO constellation basics, as most of us here understand LEO quite well. I'll just skim through some of them. I'll then talk about my past work on LEO topology design. Next, I'll introduce you to a simulation and visualization framework for these networks that enable broader community research in this area, while also quantifying the congestion control and routing challenges at a finer granularity. All of this is part of my PhD thesis work done at ETH Zurich. Finally, I'll talk about the idea of deploying a global testbed for these networks to run experiments at scale. So let's start. So when it comes to these massive LEO networks, SpaceX Starlink and Amazon Kuiper are the larger ones. But beyond these two mega constellations, various companies and startups have joined this race and have their projects at different levels of maturity. SpaceX has already deployed more than 2,500 satellites in orbit and started offering services in more than 25 countries across the globe. While they're currently deploying 60 satellites per launch, with Starship, this number might soon go up to 400, thus leading to an incredible cadence. So some of us might think, isn't satellite networking old? We just had this question, right? So what about HughesNet, for example, that has been serving customers for tens of years? Note that there have been some significant changes that make new space satellite networks special. Instead of having tens of satellites, these networks plan to deploy thousands to tens of thousands. Instead of serving a few niche like satellite telephony or the aviation industry, they aim to serve the larger community by connecting them to the internet. Satellites are being deployed at low Earth orbits instead of geostationary orbits, which are significantly further away from the Earth. So these changes are driven by three fantastic recent advances in space technology. Reusable boosters, which come back to Earth after launching rockets, thus significantly reducing launch costs. Significant reduction in size and weight of satellites, thereby packing more satellites per launch, again reducing costs. And automated link tracking, which enables inter-satellite laser communication. Products offering laser inter-satellite connectivity at 10 to 20G at distances up to 8,000 kilometers are already available. But what are all these developments leading up to? The primary goal is to provide global low latency internet coverage. This exhaustive coverage promise comes at a time when 49% of the global population is not yet connected to the internet. More than 600 million people have no cellular coverage. More than 5 billion people are far away from fiber. Remember, in places like Philippines and the Himalayas, it is challenging to lay fiber. In 2020, more than 99% of students in low and mid-income countries were affected by the pandemic. Less than 1% of retail sales are made online in Africa, while the market is huge. 90% of the Earth's surface is not covered, while the IoT demand is quite high. LEO broadband is said to not only drastically improve internet coverage across the globe and address these demands, but also enable long-distance, low-latency communications. Now let's do a brief primer on these proposed satellite constellations. How do we describe a LEO constellation? And what features distinguish this setting from traditional terrestrial networks? The first descriptive parameter I'll mention is altitude. A geosynchronous or geosatellite has a height of 36,000 kilometers, and the minimum round-trip times or RTTs are nearly 240 milliseconds. Low Earth orbit or LEO satellites, on the other hand, fly at heights between 300 and 2,000 kilometers, thus reducing RTTs by more than 60x. Another descriptor is orbital inclination. Each orbit here has several satellites. While polar orbits traverse over the poles, orbits can also be inclined. Inclination is the angle between the orbit and the equator. Here, the inclination is 53 degrees. Inclined orbits restrict satellites over densely populated lower latitudes. For polar orbits, this inclination is 90 degrees. While satellites use radio for communicating with terrestrial ground stations and terminals, Laser or radio links can be used between satellites, with laser offering higher data rates. Typically, there is a north, south, east, west connectivity pattern, which I'll refer to throughout as plus grid. A key feature of these constellations' promised connectivity is lower latency over distances beyond a few thousand kilometers. In this example, we see a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being roughly 2/3 in fiber compared to free space means that the fiber path will be 3x higher latency. If we compare the RTTs between the 8 most populous cities over today's internet to the estimated propagation RTTs over a plus grid constellation consisting of 1600 satellites, the estimated RTTs are 70% lower than today's internet at the median. So if the current RTT is 100 millisecond, the estimated RTT is 30 millisecond. Note that this is not exactly an apples to apples comparison, as we did not consider latency inflation due to encoding, error correction, and other factors. But even a 100% increase in this estimate would result in an RTT of 60 milliseconds, which is still significantly lower than today's internet. Let us now explore the system dynamics of these constellations. Satellites move very fast relative to the Earth and with respect to each other. If a satellite is now over eastern Brazil, in 6 minutes, it will already reach Africa, crossing the entire Atlantic, traveling more than 450 kilometers per minute. Such highly dynamic behavior translates to links becoming infeasible in minutes. I'll now briefly introduce you to my past work on LEO topology design before I dive deeper into measuring LEO. This work was published at CONEX 2019 and received IRTF CNRP 2020. We explored a crisp question: how can we connect satellites in order to offer higher aggregate bandwidth, keeping in mind the dynamics of the system? I'll now discuss what are the constraints we considered and assumptions we made. The key constraint of a LEO system is system dynamics, satellites flying fast relative to the Earth and to each other. But we have other constraints as follows. Setting up links can take a few seconds to tens of seconds, during which time the involved communication units cannot transfer data. Hence, it's important to minimize changes in which links are connected. Also, the maximum number of ISLs per satellite is limited. In our work, we consider 4 ISLs per satellite following all FCC filings, but we believe our methods can be extended for other numbers. I'll also lay out the assumptions we are making in solving the inter-satellite topology design problem. We assume that the satellite trajectories are given. We rely on FCC filings by SpaceX and Amazon that describe these trajectories. Knowing what precise traffic will be served on these constellations is difficult. Our evaluation uses traffic matrices drawn from intuition, but the same approach can be used for arbitrary input traffic. Our focus is on the satellite-to-satellite connectivity. So we assume that the ground satellite connectivity follows a simple range-bounded model. We treat plus grid connectivity, which I already touched upon earlier, as our baseline. On that last point, plus grid being the baseline, what are we trying to improve? One drawback of these very local links to adjacent satellites is that one requires a large number of hops to reach distant destinations. On each hop, the end-to-end communication consumes resources, limiting the network's throughput. It does like to build networks that give short paths, but also admit high capacity. We don't need to stick to plus grid's very local links. The key constraint on ISLs is for them to not dip into the mesosphere. This is the atmospheric layer that extends to about 80 kilometers above the Earth's surface, beyond which there is no water vapor present. Given the altitude of satellites, in this example 550 kilometers, using simple geometry, we can calculate the maximum permissible ISL length, which is about 5,000 kilometers here. This observation opens up a large design space. While at small scale, with few tens of satellites, only simple connectivity was possible. In the large proposed constellations, each satellite can now talk to many more satellites. We are still restricted to being able to connect to only a few, though, limited by the maximum number of ISLs per satellite. In picking the particular subset of links to connect, what should we optimize for? We use simple intuitive traffic matrices for our evaluation. We picked the 1,000 most populous cities and used a population product traffic matrix. Let C1, C2, and C3 be 3 cities with different populations. The traffic between city pairs is proportional to their population product. We also tested a variant which relies on GDP instead of population. Recall that I earlier mentioned stretch and hop count. Stretch is the inflation in latency over the minimum possible, that is traveling the geodesic at the speed of light in vacuum. Hop count accounts for resource consumption and hence congestion. In the paper, we show that lower hop count translates to less congestion in these networks. We also define an aggregate metric as a linear combination of stretch and hop count, with alpha being the weight or importance of stretch. Superficially, this seems like a traditional network topology design problem. These are known to be hard even in static settings, but a variety of heuristics are used in practice. One key contribution of this work is showing why known techniques used for designing terrestrial networks don't work here. We tried integer programming, but it suffers from two major shortcomings. It is limited in scalability. Runtime is greater than 2 days, even for 25 cities on a beefy machine, and the estimate is roughly 10 to the power of 29 days for 1,000 cities. But even if we manage to speed up the ILP by a large factor or use appropriate approximation techniques, there is a more fundamental issue here. The set of ISLs, minutes apart, are more than 90% different. We should remember that ISL setup times are few seconds to tens of seconds. So even if we could speed up the ILP by a large factor, the set of optimal links will vary significantly minute to minute. Hence, to maintain optimality, the system would need to break and make a lot of links continually, resulting in significant disruption of connectivity. We also tried random graphs, as they are shown to be useful in other settings like data centers. Although such random graph generation is a lot faster, it also suffers from large number of links becoming infeasible within a few minutes. Regaining lost connectivity is not straightforward, and one would need to break and make many links. Additionally, random graphs are very inflexible and do not allow the operator to decide on the operating point. They simply yield one combination of stretch and hop count without any control over which dimension to optimize for. So where do we go from here? This, and this picture have something in common. They illustrate the use of structure and repetition for design, in this case, visual design. We apply the same idea of repetitive geometric structure to network topology design. Consider the 1600 satellite constellation. This is the field of view or connectivity for one satellite, which goes beyond plus grid. A motif consists of two links with two other satellites, and this pattern can be repeated throughout to build the network. Note that in this case, two link motifs are sufficient, as remaining two would be filled by other satellites connecting to this satellite. One obvious benefit of using motifs is the fact that they have minimum link churn. Nearby satellites in adjacent orbits move together and are always in the field of connectivity of each other and can remain connected continually. We have analyzed 3 different constellations in the paper. We focus here on the 40 squared uniform constellation. You can refer to the paper for other results. Here we plot the average hop count along x-axis and average stretch along y-axis for the different motifs. Note that both stretch and hop count are weighted by the traffic matrix, in this case population product for city pairs. Also note that the x-axis does not start at 1 for clarity. Different motifs offer different trade-offs in stretch and hop count, and we can see a Pareto frontier of motifs superior to the rest in both stretch and hop count. Not only do motifs offer performance better than random graphs, they also provide higher flexibility to an operator. Note also that the random graph solution suffers from link churn. Okay, all right, so where is our baseline plus grid in all of this? This is where plus grid operates, with the best available stretch, but very high hop count, thus being a low efficiency motif. Note that the slope of this frontier is small enough on the right side such that by sacrificing 2% stretch, one can improve hop count by 32%. This is one of the resulting motifs for the 40 squared constellation that provides much higher efficiency than plus grid using a combination of long and short links. I'm showing the 2 links in the motif in different colors here for clarity. Our paper has many more insights though on how to design LEO topology with multi-motifs, leveraging the unique geometry of the constellations. With multi-motifs, which is explained in details in the paper, these are the performance improvements above the baseline plus grid connectivity. Starlink sees more than 50% improvement over baseline, while Kuiper also has similar benefits. We also considered settings where links need to be shorter due to power constraints instead of just the visibility constraint we considered thus far. In the most pessimistic case, a constellation must at least allow link lengths that suffice for plus grid connectivity. Even in this worst case scenario, Starlink sees a 40% improvement over plus grid. There are many more open research problems in this space, which needs to be quantified and addressed. While we already talked about topology design, what role has satellite trajectories to play in offering internet connectivity? How do we address both intra and inter-domain routing given path and link changes in these networks happen continually as the satellites move? How can end-to-end congestion control adapt to even noisier congestion signals? And how would one design applications that efficiently leverage such satellite connectivity? We need software to simulate the fine-grained behavior of these LEO networks so that we can deeply understand the problems and new research ideas can be evaluated. We built Hypatia, which is a simulation and visualization framework for low Earth orbit satellite networks. Hypatia takes as input satellite trajectories, inter-satellite topology, and ground station locations. It then outputs both the results of packet level simulations as well as visualizations that help understand the results and to develop intuition about this new context. Although the Hypatia paper discusses multiple constellations in the light of many challenges, in this part of the talk, we stick to Amazon Kuiper's first shell operating at a height of 630 kilometers and an inclination of 51.9 degrees. It is a uniform shell consisting of 34 orbits and 34 satellites per orbit. Inter-satellite connectivity is assumed to be default plus grid and routing is shortest path. And we assume ground stations deployed in the 100 most populous cities. All links are assumed to operate at 10 megabit per second and without packet loss. Paths in LEO networks evolve over time. Compare this path now to a few moments later. The RTT reduces by about 30 milliseconds here. We examine the end-to-end path from Rio in Brazil to St. Petersburg in Russia. The red shaded region has no connectivity. We found that for this period, St. Petersburg does not have any visible Kuiper satellites at sufficiently high angle of elevation, which obviously results in the satellite network path being disconnected. This plot shows the RTT fluctuations over the first shell of Amazon's Kuiper network for the shortest path between Rio and St. Petersburg. This is one example of the path elongating and two of the path shortening. Please keep track of these markers for the next few slides. Green is good, that is the path becomes shorter, and red is bad, that is the path becomes longer. For loss-based congestion control like TCP New Reno, the impact of the fluctuations is relatively minor in terms of rate. The path shortening causes reordering with latter packets arriving before ones transmitted earlier. This is interpreted by TCP as loss, resulting in a brief drop in throughput. Delay-based congestion control, TCP Vegas here, suffers catastrophically though. With the path elongation interpreted as queuing and congestion, it backs off dramatically and achieves very little rate even though the network is empty. The takeaway is that both loss and delay-based congestion control schemes can be affected due to the continuous path latency changes and reordering of packets in the network, happening not due to congestion, but predictable path changes over time. While loss-based congestion control keeps throughput, it does so at the expense of latency by building up buffers. And this is counter to the low latency objective of these networks. Also, they perform well only with an assumption of an ideal channel with no packet loss. We did this deliberately to carve out the impact of just the LEO dynamicity. I think there will be talks later which combine both LEO dynamicity and packet loss due to weather, handover, and other factors. It is also important to understand the result of interactions between traffic flows in such networks and the dynamicity of the network itself. Although for an individual city pair, link or path changes happen at the granularity of tens of seconds, across the network, changes are more frequent. Thus, as links fly over time, they see different sets of flows to them, thus changing the congestion scenario. An uncongested link, due to the change of its position over time, can see additional traffic, thus becoming congested after a while. In order to quantify this impact, we conduct a very simple experiment, sending long-running TCP flows between pairs of ground stations over the shortest path. Each link in the network is set to 10 megabit per second, and we send long-running New Reno flows between a random permutation of ground station pairs. We focus on the Rio to St. Petersburg path and make sure not to make the first or the last hop the bottleneck so that we can focus on the ISL network's behavior. Y-axis represents unused bandwidth, which is the path's link capacity minus the utilization of the most congested on-path link at any time. In a static network with fixed routing and a fixed set of long-running TCP flows, we should expect the unused bandwidth to be small. Just measuring link utilization is uninteresting. A link's utilization over time simply reflects its local environment as it moves across the globe. The static network TCP behavior is shown as the gray line in the plot for the topology frozen at its t equals 0 position. As we can see, unused bandwidth is typically small along the lines of expectation. However, we find that in a dynamic Leo network with cross traffic, the amount of unused bandwidth is larger than in the static case. Even until 155 seconds, when the disconnection happens, the dynamic case leaves 1.8x more bandwidth on the table than the static one. The reason for this difference is the shifts in cross traffic resulting from path changes. Links constituting a ground station pair's shortest path change over time. And for each link, the set of ground station pairs it is used for changes as well. This implies that the traffic mix at any link is highly dynamic, making it difficult for transport to adapt. The takeaway is that Leo networks present new routing, TE, and transport challenges. Routing and traffic engineering could be planned ahead such that knowing the upcoming changes in paths, traffic can be shifted a priori from links that will become bottlenecks soon. As is typical for any simulation infrastructure, we could not fully anticipate the needs of novel proposals for Leo networking in the future. Nevertheless, regardless of how the additional design details are filled in, as more information becomes available, the RTTs are going to vary, congestion control is going to see noisy loss and delay signals, and the shifting paths pose clear challenges for routing and traffic engineering, as quantified in this work. So Hypatia provides a useful starting point for Leo networking research. While no one can deny the utility of simulations in network experiments and beyond, even in order to make such simulations highly realistic, one needs to understand how these networks work in practice at scale. Hence, it is important that we build a global measurement testbed for Leo networks at this point, much like Planet Lab or Measurement Lab for the terrestrial internet. Here are screenshots from some network performance reports shared by Starlink users in social platforms. Note the difference in performance across these reports. In Leo networks, such performance differences might arise due to the extreme temporal dynamicity, the geometry of these constellations, and the continuous deployments adding more satellites to the fleet. Of course, there are other factors as well, much like in terrestrial internet. In order to understand the impact of Leo dynamics on network performance, we need a distribution of endpoints across the globe. These nodes can be hosted by universities, companies, and by volunteers who have access to terminals. And the nodes should be able to access each other and also cloud servers as needed. Of course, such a platform will need reasonable management, administration, and orchestration to run at scale and need some engineering groundwork. Beyond simple speed measurements, the testbed will allow us to understand the impact of low latency on application QoE. Remember the simulation result that we discussed before? Leo RTTs could be significantly lower than today's internet latencies, and it's important to measure the impact of this improvement at scale. What does Leo connectivity mean to cloud applications, including the low latency ones like cloud gaming? Leo's low latency does come with some concerns as well, one being the latency fluctuations due to the fast-moving satellites. On the top right plot, we see in simulations again that the ratios of max and min RTTs for some paths might be as high as 2. The visual below shows how dynamic the field of view and last mile latencies will be for a Starlink user in Delhi. The x-axis is the panoramic view of the user, while the y-axis is the observed altitude of satellites. Hence, as I touched upon earlier, it is critical to understand the impact of such latency variations on transport and end users QoE. As we discussed in the context of Hypatia, it is important to analyze the impact of temporal path changes and latency variations on end-to-end congestion control performance. We have seen in our simulations that different Leo paths have uniquely different properties, and hence it's worth running transport experiments at scale over these networks. In large parts of the world, people might soon have access to both high bandwidth terrestrial fiber and low latency Leo. How do we leverage such multi-access connectivity to improve application performance? Finally, such experiments at scale will help us understand the impact of weather, geometry, and long-term evolution on LEO network performance. I personally believe that the LEO networks research community has reached a critical mass to build a consortium and deploy a global testbed similar in flavor to Planet Lab or Measurement Lab. On this, we are in touch with multiple universities, including Nishant and Tim here at University of Surrey. Towards building a consortium, we took a baby step last year by organizing LeoCon 2021, a webinar on LEO satellite networks. LeoCon was able to register large-scale interest in this area with participation from 38 countries. This included more than 150 industry participants, more than 30 participants in top leadership positions, more than 100 academic participants from top 50 universities, and employees at 10 government space agencies. Gauri, Nicholas, and myself also organized an IITF 111 side meeting on LEO last year. Now that Nishant, Jonathan, and Mohammed have made great efforts to keep this brainstorming going and make this workshop a success, we must sustain this community enthusiasm, while in parallel, we take steps to set up a testbed. Mohammed and myself invite you to join LeoCon 2022, a one-day tutorial on LEO happening in Sydney later this year as part of Mobicom. With that, I thank you for your attention, and I'm open to take questions.
Yeah, looks like it's working.
Hi, it's great work. I've also been working on simulating these sort of constellations, and so I've been working on extensions to HT-Sim to do this. And even though HT-Sim is quite a lot faster than S3, I'm still struggling on the scalability of the simulations. Do you have any magic tricks as to how to simulate these large LEO constellations with significant traffic and actually simulate them for more than a very short period of time?
Well, when it comes to Hypatia, it has scalability issues as well. It's limited by NST scalability, right? So we used a single core simulation for running all the experiments. So what we found is, like, if we want to simulate 10 gigabit per second for 10 seconds, that is 10 virtual seconds. For UDP, it takes roughly 30 minutes. For TCP, it takes roughly 100 minutes. So the slowdown factor is quite high. But at the same time, what we understood while running these experiments is that we don't need to run simulations continually in order to understand the corner cases or the interesting cases happening. So for that, we can rely on coarse grain simulators or other kind of studies in order to find out when in time will be interesting events happening. And then we can simulate just for that window. And in that way, we can, address some scalability issues. It's a hack, but it works.
Yeah, I guess I'm struggling in a similar way. It gets difficult when you try to actually simulate cross-traffic interfering with each other within the network. So you need many flows, not just a single flow, which I can do. And I don't really have any great answers to how to do this without actually just trying to build the damn satellite network. But I think this is going to be a challenging area for us as network researchers as we go forward and trying to look at sort of all that, the interaction between the end-to-end protocols, the cross-traffic, the routing mechanisms that you run within the networks, and the dynamism of the network.
Yeah,
I
exactly.
don't have any really good answers.
I think we need some sort of hierarchical simulation, right? So we can leverage flow level kind of simulators for running different simulations. And then if needed, if we identify corner cases, then we can leverage something like Hypatia, zoom in and do a packet level analysis. So that simulation might make things tractable. But yeah, I agree. It's an interesting problem to explore.
So what we are doing is not exactly packet level simulation, but basically Mohammed's approach is, let's take mininet VMs and run them each as a ground station and as a satellite, and pre-compute all of the IP tables. And that seems to scale. And so it's like 1 second per real-time simulation. But the problem there is, if I want to run my own new protocol, not just TCP or BBR or whatever, then you have an issue because you have to do it in, it has to run on mininet. And so that's a lot more complicated than doing it in HTSIM or an S3 or something. But yeah, so it's a trade-off.
So will there be a talk on that? I'm pretty interested to know more.
Yeah, he's doing it.
Great.
Okay, thank you. Interesting talk. One of the question is the simulation and measurement. When you get the simulation results, how do you know your simulation results should be the realistically reflect the real measurement results?
That's a great question. I think we do not claim it's very close to reality. What we wanted to do with the simulator is that demonstrate that just the satellite dynamics, the LEO dynamics makes things interesting for the community. Now we can make the simulations realistic in the future. We can make it data-driven as we run, other experiments. If we can set up the test bed, the measurement test bed, we gather data, we make the simulations data-driven, then we might get more realistic simulations. At the moment, it's not very close to reality. As you have seen, maybe I touched upon that, we didn't even simulate packet loss in the network, and it was deliberate.
Given your simulation, what kind of traffic you use and how you generate those traffic in your simulation?
Yeah, so if you are talking about the traffic matrix, then it was a population product kind of traffic matrix. So it was simple. So once we understood that, okay, this is the traffic matrix we are going for, then we kind of created TCP flows between different pairs of endpoints. So we set up endpoints across the globe, right? This could be population centers, right? And then created TCP flows between them. These are single flows between two endpoints.
Yeah. Do you have any example of your traffic matrix? What it looks like? What's the value? Do you have any values about your more details about your traffic metrics?
Right. So it depends on different experiments, right? So for certain experiments, we just wanted to see the scalability of the simulator, and we would just run TCP flows between endpoints, right? And see what is the rate at which we could operate. Like we want to push for the limits. But then for the other part of the work that I talked about, like the topology design part, the traffic matrices we used were, population product traffic matrices, GDP product traffic matrices, a gravity model, to be honest. So that's not, again, close to reality, but that's the closest to reality we could use without getting traffic matrices from, CDN providers or content providers.
Do you have any example you can show us, what the typical value for the matrix?
No, not here, but I can talk about it offline.
Okay, I'll talk to you offline.
Sure.
Okay, thank you.
Yeah.
Hi, just a quick follow-up on that question because I'm curious. Where do you think the content is when we have a global LEO network? Do you think the content will be local, as in a few hops away and beam down? Do you think it will go down and across a fiber segment? Or do you think it will just go randomly between cities and data centers all over the world?
Yeah, it depends on how big providers go about it, right? If Starlink, for example, they are deploying inter-satellite links. So if they enable long distance communication, hopefully low latency, then people might want to use it, right? And when it comes to internet applications, of course, I see there is Netflix, there is YouTube, content closer to users, maybe a single bent pipe connectivity will work. But there are newer applications as well. Post-pandemic, I mean, these video conferencing applications, they are going big. So they require to have long distance communications, for example, or cloud gaming, where gamers are from different continents. How do we design that kind of applications and how traffic will flow over that network? So there we might end up needing long distance, low latency connectivity, and these constellations might help.
Yeah, thank you. I think this is an interesting topic as well. So thanks ever so much for raising it.
Oh, yeah.
See, one of your slides had one satellite had two links and didn't have connections to some other links. You understand what slide I'm talking about?
Yeah.
Okay. So my question is that, see that, why is it that that satellite doesn't have links to the other ones? So it's basically the broadcasting, right? So whichever is in the neighborhood should be able to listen to if they tune into that frequency, right?
Yes.
Why would they choose not to listen to this guy?
Right. So this is not, at least the inter-satellite part is not broadcast. So this is laser, and you have these laser terminals which need to rotate and align and then set up the laser link. So you can assume these to be like single links, unicast links, and not broadcast.
So this is basically link as opposed to broadcast. That's basically what I was asking. Is this is But earlier days, it used to be broadcast, right? For example, Iridium was not laser-based system.
Yeah, Iridium was radio.
Right, right,
Right.
right. So that basically determined that whoever is in the neighborhood could listen
Yeah.
if they choose to listen to that.
Yeah.
Right.
Right.
Another thing is about the topology. Once you decide this links and all that, does it change over time? So the reason is that, for example, just because the satellites are moving at a high speed does not necessarily mean the topology is going to change.
Right.
So that if you just take 2 points, even if they're moving at a speed of light,
Right.
the distance don't change.
Yep.
So just because they're moving at a fast pace, topology may or may not change
Right.
depending on their movement pattern and all that.
Yeah, agreed. So the distances would not change much, but they will soon still change, right? Because of the geometry of the Earth and the constellation, they need to cross each other.
True. The
right?
thing is that each is this going to have some communication range.
Yeah.
So it doesn't, let's say it's 100 miles.
Yeah.
So it's 5 miles or 100 miles, doesn't matter.
Doesn't matter.
But
right.
does matter if it's 200 miles.
Yeah.
200 miles, it will not be able to communicate.
Right.
Right.
Right. So I think this was one of the key premises of our solution, the motive-based solution. We actually went for that solution because of this thing, right? I mean, because if you have motives, if you have like repetitive structures connecting satellites to other neighboring satellites, then you won't need to have link churn. You don't need to address it. It gets addressed naturally because they would move together.
Yeah.
Right.
That's
Yeah,
basically what
yeah.
husband meant.
Yes.
So the topology may or may not change depending on their movement patterns
Yes.
and so on.
Yeah.
so
And
on.
we tried to find topologies which don't need to change much.
Okay, see, actually, there are some satellites which don't really change. Many people don't realize that. Actually, topologies don't change. Even these are moving at very, very high speed.
Exactly. Exactly. Yeah.
Yeah, one question. Do you consider sort of power budgets on the satellites as they move around on the links?
Sorry.
Did you consider sort of power budgets on the satellites as they're forming parts of these links and going over the populated areas?
Yeah, so for the topology design work, for the first part of the presentation is more talking about range-based models where we do not consider power as a constraint to start with. To see, so it's assuming a model where you can increase the power budget if needed in order to maintain the bandwidth. But then we realized we also needed to address the power constraint, otherwise it doesn't make sense. So we did consider power constraint links as well, where links cannot be longer than the default case, that is the plus grid case. So we could still improve on the performance just by using those power constraint links because of the geometry of the constellation and the geometry of the Earth.
Yeah, but you're assuming that your satellite effectively has whatever power you need to do that, regardless of what it's doing on the ground.
Yeah, so we assume that the satellites would be able to have a power budget at least to maintain a plus grid connectivity. Right.
Okay, I see one question here, which I'm not sure whether it's for you or someone else. John Border online asks, have you looked at OneWeb?
Good question. Yes, we have looked at OneWeb as well. We have some results. I didn't present it today, but yeah, I do have results on that.
Okay, good. Okay, so maybe you can follow up with him offline.
Sure.
On that note, I think it's time now for coffee, which has arrived just in time. So we'll take a half an hour break and come back at 15:45 for coffee.
Thanks, everyone. Thanks. Hello, how are you doing? I'm good. Good, good. Nice to see you.
Yeah, So we are sort of getting ready to start in a couple of minutes. If you can make your way back. And also we're doing this as a test bed across the Virginia Tech and Surrey campuses. So Mohammed will be doing it in person here, but there's also another pod of people at Virginia Tech who will be chipping in halfway through this. Is Virginia Tech ready now? Just check. If someone from Virginia Tech can confirm on the chat or something that they're ready to be. So I'll start talking about the test bed at least. You ready? Okay.
Can you hear me now? Okay. Okay, thank you for joining us again. So yeah, today we will present like a live demo on our testbed here in Surrey. I will first start by describing the architecture of the testbed, and then briefly go through how exactly or what exactly we're planning to show, like in terms of demos, and then I will do the live demo. So the talk will be like part of doing here in Surrey, and the other part, people from Virginia Tech will join us over the Zoom link. Okay, so starting with the motivation. So I'm asking the question why we need that sort of SpaceNet testbed. So as different speakers before me just talked about that, we don't have access to the LEO satellites actually. So if we would like to test new protocols, design new protocols, we need either to send some of these LEO satellites to the space or to have access to the existing commercial ones. And if we decided to send few satellites, it's actually expensive. It's not only from money perspective, but also from time consuming perspective and the complexity associated with that. So the other way around is to build some like a realistic testbed in order to be able to design and implement some of the new protocols and see how they perform on that realistic testbed. But another motivation is also planning a new consultation. So if you think about sending like a mega constellation, mega LEO satellites, then you need to plan them. So you need to identify the orbits, how many satellites per orbit, and you need to identify something like orbital parameters and all these information. So we need to test that before going to the space. So you need some kind of like test bed that can give you that ability to plan these consultations. So another side is that, okay, so you have a test bed in the lab, it's somehow realistic, but it cannot be like 100% real. So you need some kind of like a large scale measurement testbed or like measurement platform, like Deepu mentioned. So you need to distribute like thousands or like hundreds of like these ground stations across the world. So we can keep actively doing measurements like latency, throughput, packet loss to understand the performance of these existing LEO networks, and then feed back these information into your emulation or your software platform just to make it as realistic as possible. And then also trying and implement the new or the future scenarios like inter-satellite links. For example, Starlink now haven't implemented yet the inter-satellite links. We only have the pinned pipe architecture. So now if we want to understand how the inter-satellite link will boost the performance compared to the pinned pipe, we need to do that over some kind of like a testbed or some like of emulation, so you can compare the future scenarios as well. So for that, so we built some SpaceNet testbed here in Surrey. It has two modes. So we have a real world measurement platform. So we have access to around 6 Starlink terminals. It's distributed over like 4 cities. And then we did some measurements in terms of throughput, latency, page load time, user experience. I will talk about that in details and then in tomorrow's talk. But today I'll only focus on the emulation platform that we built here. But just before going into the details of the emulation, just to show you like what exactly we have in terms of that real measurement platform or real world measurement platform. So we initially, we built a browser extension, a Google and Firefox browser extension, and we asked Starlink user and non-Starlink user to install that extension and report the measurement that they got from their experience by visiting different websites. So overall, we have around 16 Starlink users are using our extension, web browser extension, and they are distributed over more than 20 cities. And we have 10 non-Starlink users. These are either using fiber broadband or using like cellular network connectivity. And overall, we have, like I said, more than 20 cities and over 3 continents, and we have this amount of measurement samples we currently have in our database. But alongside this plugin measurements, we also have 6 nodes, six Starlink nodes distributed over different locations, mainly again in the 4 cities. And we do active measurements like a throughput performance using different condition control. We use also latency performance from that location to different web services distributed over different continents. And also we're doing something like packet loss and how we can identify the handover strategy of Starlink. So how Starlink decide, or the ground station of Starlink decide to move from one satellite to another satellite, and how frequent is that happening? So we're using these 6 nodes to try to understand and answer these questions. So I'll talk about that in details in tomorrow's talk. But today, let's focus about the emulation platform that we built here with Virginia Tech. So just a quick comparison about the different platform that we could have for this like space network and this, space communication. So you could have something like simulation based. So like Deepopam talked about Hypatia. And you could have like an emulation that can combine both the flexibility of the simulation side and also the scalability of the emulation side. I will talk about that in details in a few slides. Or you could have also like a combination of both. So you can have some few nodes implemented in a software, and then you have also some other nodes implemented using hardware. So on hardware, I'm talking about like single board computers, could be Raspberry Pis, and also SDRs. So acts as a radio transmitters for these ground station or satellite. So you could have like one Raspberry Pi acts as a satellite, and that Raspberry Pi is attached to SDR, could be a P210 or like Lime SDR. And then there's a transmission here happening over the air. And then on the other side, you have another SDR act as a ground station, receiving that signal and then processed by the by another Raspberry Pi or single board computer. And then you could have also like measurement platform. So you collect all the measurement from the real world and feed back that into the emulation or the hardware in the loop. So what we can see here is that nothing can like tick all the boxes. So if you'd like something like scalability, so you can do that through the emulation, and you can do that through the measurement platform if you have a large number of nodes distributed across the world, but you cannot do that in the hardware in the loop. So you cannot, for example, get like 100 or 1,000 Raspberry Pi and deploy them in one place. It's costly, and also it's not that efficient. So if you want something like high fidelity, if you want to implement link layer 2, so layer 2 or layer 1, like physical layer or a MAC layer, you cannot do that by emulation, because emulation you have, or by simulation, you have everything up to the network layer, and everything beyond that is just treated as a basically netem command. So if you need something like high fidelity, you might need to go to the hardware in the loop. You might think about implementing physical layer or MAC layer on a Raspberry Pi or on SDRs using GNU radios or using this kind of tools. And if you want high realism, then simply you need to go to the real world measurements and feed that back into your platforms, or emulation or simulation platform. So what we currently have in the testbed that we built, we have the emulation mode. We have 3 different emulation modes. I will focus now on. So I'm focusing now here on the SpaceNet emulation and SpaceNet hardware in the loop. So we have like three modes. We have everything in a software. So we can simulate or emulate the whole mega consultation for Starlink or OneWeb or Telesat using everything in a software. Or we could have some of them in a software, like we could have like 1,500 satellites in a software, and then maybe 10 or 20 satellites in a hardware, as I said, Raspberry Pis and SDRs. And the third mode is just like interconsultation or intercampuses. So if you would like to have a connectivity between OneWeb and Starlink, how we can implement that. So you could do something like you have like a Starlink consultation running on one machine, and then you have OneWeb running on another machine, and then you connect them using some like an inter-domain routing or something like a similar than that, like just like a connectivity between ground stations or even satellites. So I'll try to quickly touch upon of these, and then I will present some of the demos that we have under some of these categories. But before that, I will quickly describe the architecture. So mainly this is the software architecture of the platform that or the testbed that we build. So we build everything on top of Mininet. So we use Mininet emulation as the ground base, and we build different modules on top of that. So we have, for example, we have a link characteristic module, and this is built in Python, and this is mainly meant to identify the link characteristics, either ground station satellite links or inter-satellite links. And when we talk about characteristics, we mainly talking about the latency, the SNR signal to noise ratio, talking about the throughput of that link, and all these kind of characteristics. So this module is built for that. And then we have a routing module, which is implementing different routing protocol. So currently we're implementing a shortest path routing, which is based on either latency, shortest path based on latency, or based on or best path based on throughput, or different criteria. But we implement that using shortest path now, and it's kind of like a plugin module. So you just need to change a few lines of code, and maybe you can replace that with maybe OSPF or BGP to test how it performs. Because everything is running as a VM Mininet, so it's a Linux based. So you can just implement anything in Linux and test how it performs in that setup. And then we have mobility management, and this is mainly the module that reads the TLE files and then updates them every predefined interval. It could be like 1 second, 100 milliseconds to define the new location of the satellites. And that the information coming from here is actually fit into that module in order to identify the characteristics. So if I change a ground station satellite link, I need to tell the link characteristic module that I changed that link to recompute the characteristics of the new one. So there's always communication between these two modules. And then on top of that, we have a testbed configuration, which is mainly configuring the scenarios that you would like to implement. So for example, as also Dibipam talked about, so how you would like the inter-satellite links to be? Is it like plus grid? Do you only want like the topology to be having connectivity between satellite in the same orbit or across different orbits? So all this information is configured into the testbed configuration. Here as well, you also pass the TLE files. You need to pass the TLE files in terms of if it is Starlink TLE or OneWeb TLE files, you pass it here as well. You also need to configure some information like a transmission, radio information. So what is the bandwidth of the ground stations? What are the TX power? What are the antenna gains? All this information and feedback into, again, the details of that testbed configuration. And then on top of that, you have application builder. So you have, if you'd like to build some similar application, for example, until now we build like two simple applications like iPerf application, TCP. So if you'd like to iPerf from one ground station to another ground station, you build that on the higher layer, or you can do like Bing application also to Bing between different ground stations. But this also can be extended to other things. So if, for example, if you would like to implement like 5G base station on a satellite, so you can implement it there. So for example, we have like a lot of example about that. For example, open air interface or SRSLT. So you can implement that on one of the virtual machine in Mininet, and that will be communicated to the rest of the modules that we have. And then the last two modules here, I haven't talked about. It's actually the two modules that we use to integrate what we have in Mininet as a software to the actual hardware that we have in terms of the Raspberry Pis and SDRs. Now imagine if we have like one virtual satellite, it's a virtual machine inside Mininet, and we have a Raspberry Pi act as a physical satellite. Now we have a link between these two. We have an inter-satellite link between these two. So what does that mean? That means that we need to forward the traffic from Mininet virtual machine to the Raspberry Pi. And that is happening through this hardware integration. So we implemented an interface that can move the traffic from a Mininet virtual machine to a Raspberry Pi. And then on the Raspberry Pi, there's a GNU radio module that emulate the physical layer and transmit over the air. And then in order to attenuate the signal based on the link characteristics that we compute here, we use a programmable attenuator to achieve that attenuation. So this is kind of like a summary slide on what are the capabilities of the simulation that you have, the emulation that we have. So we read, as I said, we read TLE's file from the as an input. We recompute the location of the satellites every 1 second or every 100 millisecond. So we know that every ground station, every 100 millisecond, for example, recalculate the ground station satellite links and try to pick the best one. So currently we have two different association criteria. So the ground station can get associated to the satellite that is nearest distance. And the other association criteria is actually the ground station get attached to satellite and remain attached until it disappears. And then once that happens, then it will try to reassess the available satellites and attach again. So, and again, this association criteria is just like a plugin module. So you can come up with another function for another association criteria and then plug it in and test how it performs. We compute the link characteristics, as I mentioned, and then we can run the simulation ahead of time. So for example, you can run the simulation 2 days ahead and then keep the logs for later tests. So I'll try quickly now to show you the first demo. It's a Starlink emulation. So we have Starlink Chill 1, which is something around 1,500 satellites. We deploy that already in Mininet. And then we have around 34 ground stations distributed in different cities. And what I'm trying to show you now is that I'll try to, before I describe what I'm trying to do, so what is happening in the module is that, we pre-compute everything. So in terms of routing, in terms of the link characteristics, and we save that on files. And once the Mininet, and once we run Mininet, we feed these information into Mininet, create the VMs, configure the links, and then now Mininet is running. And in the background, there's an update loop, which is update the location of satellites, change the link characteristics while we update that locations, and then allow us to do like a live demo. Like we can do iPerf from one ground station to another ground station while the update is happening in the background. So what I'm trying to show you now is that like a simple TCP iPerf session between X ground station and Y ground station, located in 2 different locations. So let me try to share my other screen. Okay, so we just now inside the Mininet. So for example, let me show you something like, so the ground station, I name it as a GS and then 1, 2, 3, 4 based on the relocation, and SAT is just SAT 1, 2, 3. For example, if I want to see GS1 and see what are the configuration, what are the interfaces of the GS1. So what we can see is here, like we have like a single interface, and that is the IP address of that interface, and this is the GSL interface. This is the ground station satellite link. So this interface is connected directly to satellite. Now the IP will be fixed, but the satellites will change. So we don't change the IP, but we change the satellites, and the satellites changing is happening in the background. Now, if I want to, for example, like pick any ground station like 29. So this is another ground station. Again, it has one interface, and this is the IP of that interface. Now, if I would like to iPerf from GS1 to GS29, so what I need to do is just simple iPerf command that we use in Linux. So just GS1 or GS29, like open the server first, and then GS1 -C, and then the IP address of that GS29. And then how long is the session should be. And then this is transmitting a TCP traffic between these 2 ground stations. So now the throughput that you are getting here is actually the throughput based on two different things. It's actually based on the link characteristics. So what are the latency between these two links to the ground station? How many hops I'm running between these GS1 and GS29? And what is the latency between these across the whole path? And what kind of protocol I'm using? So all these things identify identify that throughput. And you can see in some location, like we just have some drops in the throughput that might be due to some handovers happening or some changing in the links. So if we do something like Bing, for example, if I Bing, so this is again, I'm bringing ground station 1 to this ground station 29. So as you can see, that the latency is varying very significantly. Sometimes we can have 200 millisecond latency, or some other times we could have like 40 millisecond. Again, this is because we have an updated loop happening in the background, changing the whole path every time we change the location of these satellites. Okay, so if you ask, let me go back to the presentation. Okay, now you might ask, okay, how is that realistic? So how is that compared to the actual Starlink terminal performance? And this is what we done in the second demo. So actually, we have a Starlink terminal we have access to near London. It's somewhere between London and Surrey, and we have access to that terminal. And what we did is that we did an iPerf session using UDP traffic to identify the maximum capacity of that Starlink link. So currently Starlink implements just bent pipe. So we don't have that inter-satellite links. So we just see the performance of real Starlink terminal and how much capacity it can get over that link. And then applying the same topology, like using bent pipe, not inter-satellite links, we use that into the emulation that we have, and then configure the emulation to use the same ground station location. And we have the TLE file for Starlink. It's a live TLE file, it's not the planned ones. And then we do the same measurement again, but over the emulation. And we try to see how accurate is it. So let me show you something. So now the question is, because we don't know the association criteria of Starlink, so we don't know how Starlink decide, or the terminal of Starlink decide to move from one satellite to another. So we have here printing all the possible satellites that available to the Starlink terminal on London. So these are all the possible satellites available to that terminal, and then we compute the capacity for each one of these satellites. For example, here, so this is satellite. This is just an index 25, and this is the satellite name from the TLE files. And this is available to the terminal at London location that I just mentioned. We name it ground station 0. And then this is the available capacity of that on that link between Starlink 1563 and that terminal. And this is the latency one way, and this is the distance between these two. So we like assessing all the possible satellites available for that Starlink terminal. And what we can see here is that, so the capacity is something ranging from 200, 206, 200, so around 200 or 180. This is the available capacity from that terminal to any Starlink satellite. Now, if we want to see the actual performance in Starlink, I have it here. Yes, so this is just a simple like iPerf to a server UDP traffic. And what we can see here is that the maximum capacity that we can get over that Starlink terminal associated with any other of these satellites. And what we can see is that something very close to the performance that we can see over the emulation, something around 100, 150, 160 megabits per second compared to what we can see on the emulation around 100, 180. Yeah, so this is, it's not like an ideal scenario. So what we are doing is that we taking the information from that active measurement platform and feed this information back to the emulation in order to move it into more realistic emulation platform. Yeah, so also we did some simulation, some emulation as well for OneWeb, not Starlink, not only Starlink, and I will give the voice to the team in Virginia Tech to talk about that.
Hello, everyone. I'm Joseph, speaking on behalf of Virginia Tech. Virginia Tech was tasked of changing the application from Starlink, the default, to OneWeb. There were multiple configurations within the code that I had to change. First being the number of orbital planes. I found this number to be 12 on their website. Second was the number of satellites within each orbital plane. This was determined by first the number of satellites listed on the OneWeb TLE data. The total satellites for OneWeb being deployed right now is roughly 425. So to determine the number of satellites within each orbital plane, I had to basically take 425 and divide that by the number of orbital planes, and that would give you the number of satellites within each orbital plane. The inclination angle can be found on the OneWeb's TLE, is roughly 88 to 89 degrees. And then I also had to recalculate the ground station to satellite links, since the OneWeb constellation is further away from ground station and satellites. I also had to change the URL as well, since it's reading Starlink TLEs instead of the OneWeb TLEs. Right now, I'm going to go ahead and share my terminal to show you the process of how or what it looks like with OneWeb. All right, so Mohammed kind of gave you the basics of how to use the application. For maybe some users who don't know how to start it, you basically have to first install the application itself and its dependencies with it. Most of the properties that I've changed to switch from Starlink to OneWeb is mostly found in the mobility directory and also the controller directory as well. To begin just running the program, you would just go to the controller directory and then simply run the program as this. I did a fresh run a couple of days ago, and since I decided to do, or me and Mohammed decided to do a 1 hour simulation, that roughly took about 4 to 5 hours of processing and computing all the routing tables and the IP assignment. But about 5 minutes before the presentation, I decided to do a fresh run equals false. So that basically shrank from 5 hours to basically 5 minutes of the application being able to deploy. So after entering this, you will see something like this on your screen. You'll see that a bunch of satellites, either OneWeb or Starlink, being sorted into orbital planes. This one's the first one, the second one, etc. After that, you'll see something similar to the Mininet infrastructure, where it'll create the network or create the topology, first adding the hosts, adding the links, configuring the hosts, adding the virtual switch and controller, and then generating the IP routes and also deploying the IP routes to the satellites. And then after this point, you get to the part where Mininet is actually opened within the terminal. Other than that, we'll be able to use the same commands as Mohammed has shown you, such as ping and iperf.
Devin at Virginia Tech, and our next topic is integrating the hardware to the platform. So at Virginia Tech, we have a workstation running the MiniNet simulation platform, and then we're integrating through a network switch the user software-defined radios and Raspberry Pis as these hardware nodes. So in the diagram on the right, you see the green network switch, and then attached to that network switch, we have 3 ground station nodes on the left, and then 3 satellite nodes on the right. And their RF links are through the software-defined radios, and it goes through the programmable attenuator. On the far left is our initial hardware setup. You see a blue network switch, and then Raspberry Pis on either side, and the white items are the USERT B210s. Those are EDIS B210 radios, and then connected through the programmable attenuator. So our next slide. Just click through those arrows. All right, so currently, as you saw in the previous slide, we have 2 Raspberry Pi set up with 2 USERT B210s. The Raspberry Pi is running GNU Radio, which is an open source software-defined radio platform that interfaces to those radios. We have a flow graph that's running a SpaceCom compliant flow graph that implements a waveform that we've used on previous small sat projects. So we have an RF link between those 2 nodes. And this time I'll share my screen and show you a demonstration of what we have running. It's somewhat manual in nature because we're using, it's a command line driven interface, but I'll automate that soon. I have here, I have multiple terminals open. The 2 terminals on the left, the top one and the bottom one, those are SSH sessions into our Raspberry Pi nodes. And then the 2 terminals on the right are Python scripts that generate our TCP packets that go into the flow graphs on the GNU radio. Those generate our messages, our frames that's going to go over the RF link. I have 2 sessions of GNU radio running. So this is on Raspberry Pi 2. Run this flow graph, which connects to the radios. First radio link. Start the second one. Now we have 2 radio nodes streaming. We'll turn on the max hold so we can capture activity on these. I'm going to run the Python script to generate the TCP frames. I haven't yet sent any messages, so this will be the first one. There we saw that max hold captured that traffic coming across that transmission, or actually reception there on the receive spectrograph. Now we'll send one through the other link. We see the same. You'll also see in the waterfall diagram in the bottom left, watching this waterfall diagram here, you see the frames come through. There's 1, 2, 3, so on. And, go back to the slide. Mohammed, you can switch back to the slides now.
Yeah, I think you need to just stop sharing, maybe. Devin, can you please stop sharing so I can share my slides?
Yeah, we're working on it now.
Yeah, thank you.
Okay, so next steps, like I said, that was just 2 nodes, 2 hardware nodes in the loop. And so we're going to add altogether 6 nodes. We need to automate the communication between the community of flow graphs and the mini-net simulation. And then we also plan to update the communication protocol that we're using to more of 5G or something more similar to some of these constellations we've been talking about, and implement the methods for doing physical layer measurements. Next slide.
Yeah, I just would like to conclude that set of demos by talking about the future thing that we're currently working on. So it's basically the inter-campus connectivity. So the idea is that, as I mentioned, if we have like one Starlink consultation running on one campus, like in Surrey, and then the other constellation on OneWeb, so how we can connect these inter-constellation or these multiple constellation with each other. So there are multiple topologies for that. So either you can think of it as you can have like a common ground station or a gateway ground station on each one of these consultations, and then you route the traffic from like Starlink gateway to the other gateway on OneWeb, and these 2 gateways are just the ground stations. Or you can think of something like more complex, is that having like the satellites themselves to be as a ground as a gateways, and that will need some kind of like an inter-domain routing between 2 different consultations. So this is something that we're working on now. So trying to find what are the best strategy and how we can vary between these two approaches. And then on a larger scale is to not just running over 2 campuses, but can we do that over like more than like 2 partners and more than like just 2 partners. Yeah, and then that's conclude the demo. So happy to take your questions.
Which are probably pertinent from online, which we will go to first, and then we can come to the questions in the room. The first question is your routing flat or hierarchical? So maybe you could tell about how you do the IP tables.
Yes, so we're currently doing like a simple routing. We do static routing. So we basically doing a routing from any node to any node. So it's like from a single ground station to all the possible nodes on the network. And then we just use like a shortest path. So it's kind of like flat routing.
And many other related questions, I probably read out all of them together. So if it is flat, are all nodes and links in the topology? If it's hierarchical, that does not apply. And how large are the forwarding tables on the intermediate satellites?
So forwarding table is very large. So I can simply tell you like a Starlink consultation, this 1,500 satellites generating something like 1.5 million links. So yeah, so this is it's a large routing table for each node.
So this is where the pre-processing takes a few hours, but
Yes.
once you have it done, it's real time. So
Yep.
it's 1 second of simulation time for actual 1 second of connectivity. There's a comment that Flint is probably better than iPerf as a more powerful testing and visualization tools. And then a related question to the previous questions, how do you deliver the routes to the satellites? Is it in-band or out of band?
So currently the routes is kind of like computed centrally. So we have a centralized node that compute the routing for each the nodes in the network, and that is fed into the mainnet from that centralized node. So it's more like a centralized routing other than not a distributed routing.
There's a question possibly for Devin or for you. So is your simulation assuming full duplex operation?
Yeah, maybe Devin will answer that better.
Devin, do you want to answer?
Yeah, so Currently, it is not full duplex, but we do plan to implement full duplex in the future.
Yeah, so it's yeah, not full duplex yet. So any questions? Yeah, there's a bunch of questions here.
Yeah, it did.
Just a quick question. Thank you for the demonstration. It's interesting. You mentioned sorry, it's a Starlink in Virginia is OneWeb. Is that a real satellite link or just simply the emulated link?
So it's mainly the consultation. So it's so we can configure like one consultation on one campus and then the other one on another campus. So
okay.
It could be like the inverse way. It could be Telesat. It could be any kind of consultation. We only need the tele files, and we need to input that tele files into the emulation, and that will form the mininet configurations.
Okay. So the emulation, how many machines you use to emulation in the storage side?
So on server side, we have like 1,500 virtual machines inside
100 virtual machines.
inside Mininet, and then we have like 35 ground stations as a virtual machine as well. But we can go up to 4,000. And a single.
That's all these virtual machine running a single machine.
A single machine. Yes.
Okay, that's the performance could be difficult. But how you link between these two? One is the virtual machine, emulated in Surrey, and other in Virginia. One way, how will you link them together?
So currently, we're working on our simple approach, which is having two ground stations on both consultation act as a gateway. So we have one ground station as a gateway here and one as a gateway here. And then we connect these two over SSH tunnel between the two campuses. And we route all the traffic inside that tunnel. For example, if ground station number X here want to bring ground station number Y, the only thing is that it needs to go to that gateway, and that gateway will forward the traffic inside the tunnel to the other consultation.
Okay. Just a demonstration, the talk is go through this emulated environment or just the Zoom link?
So sorry, I didn't get that.
The conversation between us and the Virginia side is via this connection, or it's just the Zoom link?
No, it's an SSH tunnel that we established.
Okay. Great, thank you.
Yeah, so nice talk, nice demo. You mentioned the possibility of using satellites as gateways, right? So like for connecting, for peering with other satellite networks. So I think this question is exploratory, but do you think like you'll need to have some designated satellites which could do this peering? Or how do you go about it in order to scale things reasonably? Because I mean, there could be issues with BGP convergence and stuff, right? So what's your opinion on that?
Yeah, I think one way maybe to think about it is maybe you could have like one gateway satellite in each orbit, and that will be like a fixed satellite, and then you move the traffic enter the domain to that satellite in order to across the domain. So it could, but then again, the routing table need to be updated very fast in order to maintain that connectivity. But yeah, I think this is something still needs some investigation and preparation.
One more online that we can approach. And by the way, Devupam, the convergence is actually a huge issue because it takes a few minutes for convergence to happen. So you have to somehow pre-compute the forward tables, and because you sort of know where the orbits, what the orbits are and where the locations are going to be, you can do some of this buffered rather than online. I think that's the only way, probably.
Yeah, maybe to add on that, so our initial very early study about using OSPF inside that 1,500 satellites shows that every 1 second change in the satellite location need like 3 seconds to converge the routing table across all these satellites, which is very, very time, yeah.
Yeah, and I imagine I don't know if satellite to satellite interconstellation connectivity is ever going to happen, right? But I imagine that there's probably points where for a given pair of constellations, there's like a point where there is good inter-satellite link can be established. And then whichever satellite happens to be close there, that's probably where the interconnection is going to happen. And that's the gateway point is going to change. And that update has to go to the entire constellation somehow. And that's probably another source of complexity for this. So there's a question about, do you plan to run any link state protocol with your routing module in conjunction with the ISLs and dynamic topology change?
Yeah, I think this is the good side of using Mininet, because Mininet is just a virtual machine using Linux. So if you have an implementation for link state routing protocol, you just need to plug it into that virtual machine, and you can test it and see how it performs. We haven't tested that yet, but it's something on our agenda to try.
There's a question about how are you going to transfer data between the two campuses?
So we thought about that initially by using kind of like VPN or SSH tunnel between two machines across the two campuses. And then we do that, we forward the traffic inside that tunnel. But in order to do something like more scalable, we thought might be the cloud-based server might be a better approach. So if you would like to have more partners, then we will have one of the main servers, or one of the main consultation running in one server, which is cloud-based, and then we have other partners running other consultation, and we just go to that over like another VPN tunnel for each one of these. But yeah, so it's still something we investigate. So either just an SSH tunnel or cloud-based approach. So something is still under the way.
Okay. So another clarification question. About how do you have to store every end station address in a formal forwarding table? So does that mean billions of end terminals?
Yes, we have to store everything. Yeah.
Currently, because of your static routing.
Yeah, static routing. Yes.
I think if you go from there to something more slightly dynamic.
Right. So maybe I can quickly show you how that looks like. So for example, if I want to see like satellite number 10, and then just simple routing. Oh, sorry. Yeah, so just sat number 10, and then I would like to see what is the routing table looks like. So here's the routing table. So still up there, but I cannot scroll up. So it's very huge routing table. So yeah, it's just because we are using static routing now. So we store every IP address to every node in the network. So as I said, we have like 1.5 million links for that 1,500 satellites.
Also, you keep updating that routing table based on where the current location is.
Yeah.
And can you remind me how many updates happen per second?
Let me show you something.
Peter Ashwood is saying it doesn't seem practical at all. And to that, I can answer, yes, it is practical because we are actually seeing 1 second of simulation per 1 second of real time. So as long as you have enough horsepower on your server, you should be fine. And we have a normal server. So
Nishant, one question is like routing tables could be computed as well, right? I mean,
that's exactly what we're doing. So routing table is, so there's about 4 or 5 hours of pre-computing that's happening. And then every second of simulation time, all you're doing is changing the routing table to what is current. And that's all you're doing.
Yes, so exactly. So what we do is that we pre-compute everything inside a folder, and then we save everything in a file. So for example, if we would like to see the routing, so it's saved here. So these are all the possible routes for every satellite and every ground station. So what we also have is that, so if I cd to here, so what we have here is this is the routing table updates. So just on like a batch file that we run every predefined interval where the satellite changes location and reconfigure the routing table for each satellite. So if we just open one of these, so like sat10 dot. So what you will find is just like normal IB route updates commands. So we just do that every time we change the inter-satellite links or the ground station links.
Hi, I've got an easy question and maybe a more difficult question. But the easy question is, do we know what any of the LEO operators are actually doing? Are they pre-computing I mean, I think these are forwarding tables that are pre-computed. So are they pre-computing forwarding tables and uploading them to their infrastructure, which is how I build it, or are they actually doing something dynamic? Do we know?
No, we do. You mean Starlink?
Yeah, well, I don't mind who, but
Yeah.
what are the people who have a big network? Probably them.
So I think Starlink now doesn't do layer 3 routing.
Yep.
So the only thing is that they go up to the satellite and then to the ground station. So they don't have a layer 2 routing, just a forwarding, like a switch. Just receive a bucket and put it there. What we're trying to do here is like kind of like simple layer 3 routing, but it's if we want to have something more dynamic, that comes with a trade-off of the we need a like fast convergence routing protocol. So this is what we haven't tested so far, but yeah, for a current implementation of Starlink, it's just a bin pipe switch. Yeah.
So the second one was the tricky one, which is how can you make that manageable? I mean, I've run operational networks, and having a routing table that big would make me die, because when somebody complains that traffic isn't getting there, I would kind of go, well, I don't know. But you can't do that to a customer. So how are we going to actually scale this and manage it? Because this dynamicism could actually be a real problem rather than an advantage. So have you thought about how we manage it?
Yeah, so this is a tricky question. Yeah. Yeah, I think it depends on how fast we need to change and how fast this inter-satellite links changing actually. So it might be the case that these inter-satellite links between each other doesn't change that frequent. So might need to do that very frequent update. The only thing that you need to just update is just the ground station satellite links. And that is very simple because you just change the gateway. So you just tell that ground station, your gateway becomes SAT2 instead of SAT1. But if the inter-satellite links doesn't change that frequent, then it will not, I will not say it will be easy, but still it's not that high dynamicity as, so it depends on how fast that inter-satellite links change, if that would answer the question.
I guess within an orbital shell, if you assume like a plus architecture, like what Debopon was saying, it's, well, the east-west could change a little bit, but north-south is never ever going to change, well, unless there's a failure of the satellite, right? So those sort of things somehow minimize the number of changes you need to make. And I guess use whatever solution, this is my current feeling at least, is whatever solution you come up with, you'll have to do some kind of pre-computation, and the routing table updates will be working at T+5 or T+10 minutes. And then when that convergence actually happens, you're ready to hit real time. How to manage that and what that plus delta should be, all of those is interesting research questions, I guess. I think we are sort of out of time. Let me ask one last question, perhaps from online, unless there's someone here in person. Yeah, okay, there's one question here. I'm going to go with that.
So you mentioned that Starlink just uses, goes to satellite and comes back. Why are they not using, do you have any feeling as to why they are not using these inter-satellite links?
I think they're still testing the inter-satellite links. The technology is still under development, I would say. So, but they haven't implemented, and also the question comes, if they implement the inter-satellite links, do they need like to do like layer 3 routing? If yes, then I think this is still also something not done yet and need to be explored. So it's two things: the technology of inter-satellite links and the layer 3 routing between these different routers. If we think of the satellite as a router.
So I think we should probably conclude there and thank Mohammed.
That's why this.
So we now have talk by Andy Marr and John Earl of CGI, and Andy leads the 5G programs in its space division of CGI, and his team have delivered the ESA's, or European Space Agency's, 5G 6G hub. And John Earl is the senior solution architect with over 20 years of experience in CGI's space business. So over to you.
Thanks be helpful if I spoke into the mic, wouldn't it, for anybody who's not here? Right, is that working? Can you is it coming over the speakers okay? One higher. How's that? Yeah, okay, great. Right, thanks very much for having us. Yes, my name's Andy Marr. I'm a director at CGI. John and I work in our space business, and the space business really covers, well, a whole load of stuff, but our area focuses on the one side, space operations, so looking at building operational centers for satellite operators, really on the ground segment side mostly, although also on the satellite operations side. And then on the other side of the business, we look more at the applications of space data. And actually, our area in that business sits within the application side, and we look at the integration of terrestrial networks and non-terrestrial networks. So working towards this kind of vision of 3D networks using seamless connectivity between various different types of networks. So we're going to talk a little bit about the work that we've been doing in the area and some kind of lessons learned from what we see. So I'll talk a little bit about the motivation for CGI working in this area, why we think it's relevant. We're going to talk about a couple of the test beds that we've built that might be of interest. And then John's going to talk a little bit about a little bit more deeply into the technologies that we're working with and a couple of the example projects that we've done, and then finish up with a few lessons learned from what we've done so far. Okay, so I'm going to do one boring corporate slide, but hopefully it's sort of relevant. So CGI, if you don't know, is a global systems integrator, service provider. Lots and lots of people all across the world, so sort of scary big corporation. But the reason that's good is because we can do things at scale. So a lot of the projects that we do are solving complex problems for clients that have got large issues to solve. And we work across a whole load of industries. And there's space, but all of the others are kind of relevant too. And the reason they're relevant, I think, in this context is because when we look at 5G, it's a service-driven network architecture. Okay, it's built to look at all of the applications a lot of the applications that we see in the area go across a whole load of industries. And if you memorize the ones from the last slide, you see that a lot of those kind of match up. Okay, so we're able to reach into our colleagues in different areas of the business and look at sort of practical applications of 5G with our colleagues' customers, as long as we remember to talk to them. So that's why we're interested in 5G to begin with. And then let's add space in. So as I said, our heritage is in the sort of satellite operations business and also sort of simulation. So for example, we built the OneWeb Network Operations Center. So looking at helping them operate the entire ground segment of OneWeb, the sort of 40 odd ground stations, and calculate the links between the ground stations and the satellite payloads. Okay. And what we see is that increasingly there's a shift in the way that satellite operators are thinking in terms of the standardization of terrestrial and non-terrestrial networks. So things like 3GPP, also looking at integrating satellite. The emergence of LEO constellations is obviously a big shift in the way that we talked about kind of lower latency in some of the previous presentations, but that clearly helps the integration. But they're getting more complex as well. So a LEO constellation obviously has a lot more data, satellites flying over the Earth very much more quickly. So there's a lot more stuff that you actually have to do. And so I think what the vision that we're seeing is that a lot of satellite operators are now talking about how can we make satellites more accessible to, before you had your sort of satellite phone, it's very much a separate kind of technology. You have to buy this sort of subscription to Iridium or whatever. You've got to have a particular device that works for a particular network and does a particular thing. But what we really want to get to is the point where any device can use any network seamlessly. So I guess I'll just talk a little bit about my perspective on different parts, different players, different stakeholders, what they want to get out of this. So we'll talk about users or consumers, industry operators, the satellite operators themselves, and then a bit about the environment. So from a consumer perspective, when we're talking about connectivity, just want it to work, right? I want to be able to connect my phone to the same network all the time, have a seamless experience. I want to drive to the train station, get on the train, get to the airport, get on the plane, get to my destination, and for it always to work. I don't want to have to log into different Wi-Fi networks. I mean, the percentage of people who actually use Wi-Fi on a plane is extremely small at the moment. You know, that's the kind of thing I'm looking for. So I need to be able to access that, and that might be that I can talk directly to the satellite, like companies like AST Space Mobile. I think we're going to hear a bit about later, or it might be that I've got a roaming sort of cell network that I can connect into. But that's the experience that I want. I want seamless connectivity. For industry, industry is, for example, energy and utilities, is becoming ever more reliant on data and being able to make quicker and quicker decisions about data. So if you look at the utilities example, if I've got an IoT device in the field somewhere, if my IoT device recognizes that the water level is too high or too low, I may need to do something about that very, very quickly. I've got extremely high availability requirements. So I really, really need to make sure that the connectivity to that data is reliable and quick and particularly resilient. So maybe I'll use satellite or an enhanced 3D network to make sure that even if I lose connectivity to my primary route, I've got a backup. So it's not just about seamless connectivity, sometimes it's about having multiple routes. As a satellite operator, if I'm going to be operating these mega constellations with hundreds, thousands of satellites, suddenly my data size increase. We've talked a lot about kind of how you simulate these kind of networks and the amount of data that you're processing and how do we possibly scale this up. Well, it's the same with the operators actually kind of monitoring these things. So when I was building, my team were building didn't do it on my own, the OneWeb Network Operations Center. You know, we did a lot of work with the operators who were coming from obviously a kind of non-mega constellation background, as everybody was. And they were used to a setup where you would, you'd watch the satellite come over, you'd count down to a handover with the ground station, you'd have a graph which sort of showed you normal, and you count down, okay, graph's still normal, we're all good, 20 minutes to the next handover. Where OneWeb does something like 3 handovers a second. So they can't do that anymore. They have to change the way that they think about how they monitor the network. So there's a shift in the way that operators need to think. And then there's all the sort of boring stuff about billing and capacity and how do I deal with regulations. So when you're thinking about routing data through a network, it's not just about the most efficient solution. It's actually thinking about, well, where can my data land? Is it allowed to go through a country on a fiber link through this country to get to country B? There'll be loads of examples where actually you might not be able to do that. Okay. So in-satellite links might help with things like that. When we were talking about the constraints that went into the resource manager for OneWeb, we had to talk to some government bodies about export of data. And they said, where are you exporting the data to? And we said, I don't know. Somewhere in the world, anywhere in the world, everywhere in the world. And so there's all sorts of those kind of constraints that you have to think about as well. And then just the last point on environmental considerations. Somebody told me recently that when Cristiano Ronaldo puts out an Instagram post to his something like 4 million followers, the energy used to post that in everybody's device would be enough to keep an average UK household running for 10 years. And they also told me that 90% of the world's data has been created in the last 5 years, and 68% of that data is created, used once and never again. So I think we kind of have a duty to try and think about the efficiency and optimization of the level of data that we transmit as well. So there's that kind of point which I think is worth keeping in mind. So very quickly on a couple of the test beds that CGI have built. So I'm going to talk about the right-hand two in a little bit more detail. We do have an application to terrestrial 5G center in our London office, which is a Nokia DAC solution, which is very focused on the terrestrial. But what's probably more interesting for this session is our lab in Leatherhead looking at hybrid 5G SATCOMs, and then a similar facility we built for ESA. So the lab in Leatherhead has got a couple of satellite antennas on the roof, GEO at the moment, and then 2 core networks implemented, which means we can demonstrate applications of integrating terrestrial and non-terrestrial. So we built it in some ways to sort of show clients what we could do, but actually it's become a sort of training ground and to build the team's knowledge as well. Interesting on the terrestrial side, partly because we've got constraints around what we can do in the building, because we have secure areas working with military clients and things like that. So we've learned quite a lot there. And then on the ESA side, ESA wanted a focus for 5G and SATCOM within the UK. We built them a facility where they can demonstrate to interested people, similar to the CGI facility, but also use it as an engineering playground for people to come in and demonstrate their applications and to test over a live satellite link. So at the moment, there's a Avanti and a Eutelsat link there, but we're planning in the next few months to deploy a OneWeb terminal and increase the 5G network supplied by Vodafone to be an outdoor and indoor network as well. And that facility is freely available for people to use. So I do suggest if you're interested in using it, finding out a bit more about it, and then come and talk to us, or indeed talk to ESA. I think we've got a representative from ESA later in the workshop as well. So I definitely suggest finding out a bit more about that. It's a really, really useful facility. Okay, that's me.
I discovered my shirt, but I actually hold it. Okay, can you hear me? So technologies, we build test beds and we do it to develop technology. I'm enjoying the chat. So Andy mentioned OneWeb. So we built the global resource management. So eventually 588 LEO satellites, original spec I think was about 1,000, 40 plus ground stations. And it's basically calculating the bent pipes. So frequency and power assignments across the network, tailoring in things like the supply plan. You know, which groups of users in which cells. You know, OneWeb is actually an LTE network effectively. So all those users that we're talking about within cells are connecting over the LTE network over the bent pipe. How much will they actually use? And then adapting that over the course of the satellite's orbit around the globe. Then complying with regulatory technology constraints. For example, OneWeb, as it goes over the equator, has to tilt each satellite in order to not affect the geo signals coming down to the Earth. And it's done continuously and accounts for continuously changing geometry of the network. We keep talking about the network geometry being static, but satellites come in and out of service, satellites are put into maintenance modes for periods of time. We can't make the assumption that our 10,000 satellites, even our 588 or 400 here, are all actually live at any one time. These things will change, and they will change frequently. Now, originally, this was designed to run every 8 hours. It's a pre-computation. And optimizing that over a Spark cluster, eventually it's down to the order of minutes, which becomes important because the next thing you do as soon as you have this capability is take it and start doing what-if planning and visualizing. And everything we do has to think about the fact that as soon as you've got your simulation running, and I love the Microsoft presentation, you're going to want to visualize it. You're going to want to do this what-if as well as do the operations. 5G. The focus of our test bed in Leatherhead on the 5G SATCOMs part is really focused on what can we integrate and do today. I'm afraid it's not that blue sky. We're investigating equipment, we're investigating and exploring the 5G core network radio functions that are available commercially and in experimental test beds. We're investigating bespoke routing and management, cross-domain COTS OSS functionality,
bringing telecom stuff into the space domain, experimenting with preferences, exploring satellite network capability, and building hybrid-aware domain-specific applications. So one of the things we're interested here is in looking at how we can make use of the best parts of terrestrial, LEO, and GEO, because they all have different properties and they all have their place. And our applications that we build, going back to the first slide with those different industries, have to consider where we might use those in their best case. You know, we may not choose to put, for example, the 5G control plane over a LEO satellite because the latency changes. We're looking at dynamic provisioning. I mean, if we looked at the ECSAT phase 2 item, everything ends up having to be dynamic because there are just so many different configurations we actually want to test. Yeah, there are many different partners we want to bring in and link in, and this has to be done configuration on demand, infrastructure as code principles. It's not really possible to have somebody sitting there all the time planning this stuff out. Continuing, Andy mentioned simulation. So about 2 years ago, we merged with a company called Sysys. We're very much into producing operational satellite simulators, accurate modeling of environmental, physical, and mission elements. And they've built a modular design to allow to put different payload elements in. The focus here is possibly not the kind of simulation that's being talked about today. It's really about how does this thing operate, validating operational procedures. But if you then think about in a multi-constellation context, as I move from having that one satellite to hundreds of satellites or thousands of satellites, and the looking at failure, identifying failures rather than continuous monitoring that Andy was talking about, that changes how these things work and build. We're also interested in some of the stuff that was talked about earlier with Mininet, inserting network simulation software. So at the moment, the Constellation Simulator does link budgets, it interfaces with the operational systems. There's a room there to sort of tailor this and link it into the kind of stuff I was talking about a minute ago about satellites, because maybe we don't need to simulate the whole constellation. Maybe I'm interested in simulating just, I know that OneWeb have a ground station in Southport. I know that I have a user terminal in the middle of the Atlantic. Maybe I know there's 1 or 2 ISL hops and just simulate 2 or 3 planes, just the parts of that grid plus line you need. I don't necessarily have to simulate everything or solve the, frankly, really interesting problems that you're all talking about. But then, what is the impact on the services? What is the impact on the operations? What is the impact on the applications? Another project, dynamic predictive routing. So this is very, very similar to some of the stuff you've been talking about, and unfortunately, I'm not working on it. But the concept here is really to take a wider range of measurements and start using some data science to determine optimal paths. And it's a hybrid approach. We see there will be a centrally programmable network. We're not convinced that the network itself at the moment or in the next few years is going to suddenly make all the decisions itself for these very complex routing problems. But there might be localized and contextualized routing judgments. But ideal routes will have to take into additional operational factors. I mentioned satellite power levels for a reason, because it's a nice idea that we will always have enough power. But if I first have my satellite go over, I don't know, an area of India where everybody suddenly is using it, I can't guarantee that that satellite will have the power for the rest of the orbit, and it follows on for multiple orbits after that. And these things, these operational factors linked in with the potential supply side stuff has to sort of come into a consideration. That's not to say we'll be able to solve it, but it's an interesting thing to look at. And exploitation. So where are we looking at hybrid networks? So first example, it's another project for looking at satellites on railways, but really pushed by the fact that the future rail mobile communication system is coming in, and that will change how trains have to communicate. The Ofcom, in their wisdom, have not put aside any spectrum to allow trains to use in this context, which means that other solutions will be needed. This might be an additional build out of terrestrial LTE networks or 5G networks, but there is room for potentially supplementing this with satellite, particularly in locations with very remote locations, built up locations less so. And obviously with the advent of LEO, you don't necessarily have the same view angle issues that you have historically had with GEO. Again, you end up pre-computing, and it's a problem because clearly your trains are often delayed, so your pre-computation about what might be visible may no longer be the case. So some aspect of that will have to be local, but that can maybe be done at the user terminal side. Another one, we're doing some trials with OneWeb, so looking at feasibility of 5G over LEO, and we've done 5G over GEO. Obviously, with 5G over GEO, you don't have the handovers, etc. And we've made our testbed in Leatherhead portable, taking it out to Toulouse, where effectively they have a set of different antennas from different manufacturers to trial, and a local satellite gateway, which can take over the one plane of satellites. So you get about 20, 25 minutes of connectivity to perform trials, and you have the best case LEO round trip latency, because you're no longer taking data off into space and back to Svalbard and back to the UK and London and then to your site. You're going up and down. There is a LEO GEO trial planned. So I was talking about applications. Again, it comes down to what would be useful to supplement and use these two things together. Well, maybe you, I don't know, distribute your routing information as an out of band over GEO to all your LEO satellites. And hybrid PNT is an entirely different project that's got limited relevance here probably, but this is taking two different technologies and using them to supplement each other. Again, this is taking GNSS, well-known, proven technology, lots of problems, easy to jam and block, limited vertical accuracy, but then adding positioning using 5G and passively identifying masts. There are a number of projects around this that are going on, and they're all really interesting for a problem that's actually becoming more critical day by day. And lessons learned. One slide. So what have we learned from doing these test beds? One, 5G standardization is a nice idea, but isn't there yet, I would say, in the marketplace. It's been massively affected by COVID. You will find lots of devices. I think the rollout is nowhere near what anybody expected. And this impacts us building these test beds and doing these experiments day by day. You simply can't get the devices. If you get the devices, they don't necessarily connect. And everybody's got their secret sauce that they're still not sharing. Education is required. We have promises and we have reality. We need to be focused on what, in our context, what mixed networks are likely to be good at. In the broader context, we have a great story about latency over the globe, which is fantastic for what I would say is a limited range of applications we've identified today. Video conferencing, I've been video conferencing with people, and you all have been video conferencing or having telecoms calls with people on the far side of the world for the last 20 years, and we've got on with it. Cloud gaming, fantastic, but 150 milliseconds latency, which was the best effort, is still not going to work. You're still going to get shot in a first-person shooter. There are cases where these orchestrated networks are fantastic, but we need to be realistic, perhaps, about what those opportunities are. The variable latency, to me, is a problem, and it's not a problem that's going to go away. So how does the network itself and the applications built on it deal with that? We'll always want more scale. We'll always want to go faster. And our soft factors aren't soft. While building this OneWeb stuff, the regulatory aspects meant the best case solution was not available. And that will continue to be the case. And the last slide has Andy to answer questions. So that's okay.
Okay. Thank you. Cheers. So with the PNT GNSS application, what hardware are you associating that with? Are you using an Avanti terminal or OneWeb terminal? And which generation?
So the PNT project actually doesn't use satellite. It's got a drone with the GNSS receiver, then a static software-defined radio passively looking at the 5G part, the 5G masts. We basically include it in the slide deck because it's an interesting alternative to other 5G things. And I'd probably have removed it if I'd written this slide presentation 2 minutes ago, yeah? Well, 20 minutes ago.
And on your tests to and from different operators, for instance, to and from Geo that you're doing from Toulouse, is that Osigol, I guess, the gateway in Toulouse? Is that, have you had to deviate anywhere from the 5G specs to make that work? Or are you having to?
Not at the moment. The main challenge there is antennas and IP connectivity. If you're just routing 5G control plane directly over a LEO or GEO, we've had no problems whatsoever. The fun bits come when you look at the 3GPP specs and you start trying to put either the parts of the radio access network into orbit and decide where you're going to manage that traffic and push it about.
Yeah.
Or if you want to start doing things like multi-homing. And that's the point where the commercial core networks don't really have the support and you start talking about experimental ones. I mean, we had a call today with the 5G IC here to talk about what we could actually do, for example, at ECSAT.
Yeah, thank you very much.
Okay, so we just have time for one question there from Murtaza and then one online.
Thank you. This is Murtaza from InterDigital. So I have a quick questions regarding integration with the 3GPP system. I think you already mentioned a few bits. So I just wondering what sort of framework did you use? So, you know, we have this AT3+ at the moment. So you can integrate satellite through that and it support multiple TCP at the needs. So I just wondering, based on your projects, what framework did you use to integrate with the cellular network?
I think I probably need your question written down, I'm afraid. So the integration at the moment is quite light. The interesting bits come when we start introducing the ETSI Mano, which is the orchestration tool. And at that point, you start writing bespoke functionality and hooks to make decisions about resilience and monitoring the links. As I say, the actual links between the core network and the satellite, it's a backhaul link. You know, satellite has been used for backhaul for LTE and 3G as a resilience case in the BT network for years. Okay, I think it's on 10% of sites, could be 15%. The fun bits come when you think about dealing with it in a mobile private network use case, or if you start thinking about it in the case of multi-satellite.
Sure, thank you.
Okay, just read out one question for you and online, and then we'll have to move to the next one. So this is Peter Ashwood-Smith saying, you mentioned not sending 5G control via LEO due to varying delay. So how would you send the 5G control? Wouldn't the normal deployment for backhaul be where there are no other ways?
So we can send it by LEO, and we have sent it by LEO, but it is a case of something where it might be more efficient to send it by GEO because you don't have the variation. And all I'm saying is that there will be use cases where having a known and predictable behavior is better than the higher throughput, but the unpredictable latency behavior.
Yeah, makes sense.
Thank you very much.
All right, our next speaker is Rowan Chesmer. Did I say that right? Chesmer from Vodafone, and he's a technical leader for future-looking non-terrestrial networks in Vodafone R&D development. in the Vodafone R&D department. He was responsible for trialing and developing cutting-edge satellite technologies with the aim of improving global connectivity. So welcome and thank you for being here. Why don't you do that?
Hello, can you hear me? Nope. Yeah, it's working. Okay, so as you said, yeah, it's working, yeah, okay. My name's Rowan, I'm here from Vodafone Research and Development. I'm here to talk about our exciting venture with AST Space Mobile, aiming to connect the unconnected. Okay, so what we're trying to solve, we're trying to solve basically the rural parts of the world. So there are currently over 1 billion people who are unconnected around the world, 95% of which live in rural locations. So we're talking, rural parts of Africa, the US, Canada, South America, Australia. And the reason that these people don't have connectivity at the moment is because mostly financial reasons. It costs a lot more to build these big cell towers out in rural locations, and you get, 1/10 of the number of people that come to actually pay for that connectivity. So it's uneconomical, and also it tends to be less resilient because you've got it doesn't get maintenance as often, and you get sort of worse disasters in sort of weather disasters and things like that. So I'm just going to go through one example I have, which is coverage in a town called Numbi in the Democratic Republic of Congo. The local people and engineers had to carry 2.7 tons of equipment, nearly 30 kilometers across the hillsides and the fields just to put up a base station for one village. And this took a huge amount of effort. And you can imagine this is a relatively close village, and it's a relatively large village. If you had a smaller village with less people to hike up and a longer distance to go, it would be huge or just impossible task. And then, as I said, you put all this effort in to put this one base tower in there, and then hurricane goes through and destroys it, and then it's another 3 years before you've got another connectivity tower going up. So as Vodafone is purpose-led, we want to be able to solve this issue of rural locations. And so we're going to do this with AST Space Mobile. So what is AST Space Mobile? We are going to connect unmodified handsets, so the phone that is in your pocket at the moment, directly to a satellite, which will provide 4G and 5G connectivity everywhere. So basically the idea behind it is, the idea behind it is that you will be able to go wherever you want and have connectivity. So I'm just going to go through how we differ from other satellite constellations. So Iridium is the obvious satellite phone. It's been around for ages, but you need to buy your own satellite phone, and it's relatively low data rates, and it's relatively expensive, and that's why it's had a very, very small uptake, because it's not standard. And then you've got Starlink, Amazon Kuiper, OneWeb, Lightspeed, which have really high data rates, but again, needs a phased array or a satellite dish on your building to get that connectivity. So it's relatively high cost to the individual. And then there's more IoT-based options, so they're lower cost to the individual, but again, aren't standardized. But the main problem is that they're low data rates. So they're great for IoT applications. If you're only sending small amounts of information, this is the water depth of a river or the moisture of a farm field or whatever you want to know, it's great for that. But if you want to do anything more than that, it's fairly useless. again, Skylo and Sateliot, you might have heard of them as being one of the first people to get connectivity to an unmodified standardized device. And it's great, it works, but again, it's NB-IoT only. So it gets over this sort of the concerns that you have with the swarms and the Astrocasts where it's not standardized. So you have to buy a bespoke tool for that particular task. You can just use any NB-IoT connectivity SIM and it will go from the terrestrial to the satellite and roam from one to the other and connect. But again, NB-IoT, so not huge data rates. And what we're doing is LTE, NR, direct to an unmodified handset. So you again got that 3GPP standardization, but you've got that high data rate of being able to stream videos or whatever you do currently on your phone walking around town. So how does it work? It's relatively simple in terms of basically what we do is we put everything on the ground and then the satellite is just a massive repeater. So all of the core network, all the eNodeBs, everything is on the ground. It goes to the ground station, which then converts it to a QV band up to the satellite, and then the satellite converts it back down to the LTE and NR bandwidths. So the sub-gigahertz bands and the 2.1s and 3.5s, etc. And that will go directly to your unmodified device. So that frequency is literally using the same frequency that you are using on the terrestrial. So what we do is basically we have multiple beams, like thousands of beams from this satellite, goes down to a fixed location on the ground. And then, so if you were standing in one location, you would always appear to be in the same beam. And then as that satellite disappears, the next satellite goes onto that beam. So you don't see a change. So as a user, you just are effectively constantly in the same cell as if it was a cell tower, just it happens to be in space. So we do this with a massive phased array, basically. I'm going to talk about some of the challenges of coming from space. So first one, obviously, is link budget. You know, if you're going from what is normally a couple of kilometers away to suddenly 700 kilometers away or 1,000, 1,800 kilometers away when it's down at the low elevation, because we've got that fixed point on the ground, it's actually extending that elevation much, much further. This is solved by having the biggest satellites that have ever gone up. They're talking sort of 30 meters in diameter, massive phased array up in space. It's quite a marvel of engineering, really. The next obvious sort of challenge is Doppler shift. So if you've got a satellite flying really quickly overhead, your phone can't cope with frequencies that move too far from the standard frequencies. And that will constantly be changing as you go over. So you see the top hand graph here is showing this is the field of view of a satellite and how the Doppler shift is changing. So it's up to sort of 16 kilohertz of variation from the standard. So what we do there is obviously we can predict where we are relative to our target location, and we send the frequency at the wrong frequency so that it arrives at the ground at the right frequency. So it's just a compensator, basically. Time delay, we've heard a lot about time delay issues and variation in time delay today. What we do is we've got some secret sauce that we're not allowed to talk about. But the main thing from the concerns that lots of people have is that we fix the time delay. So if the time delay happens to be lower, we just let it sit in the ground station and then we send it to the eNodeB. So whatever, we know what the maximum delay is, and then whatever that is, that is always the delay. So when it's shorter, it just sits there and then goes into the network, which stops all of the issues with varying time delay. And then the other main issues are interference. So this is cross-border interference. So if you have connectivity in one country, you're not allowed to have any of your emissions going into the next country over. And there are quite sort of strict rules and regulations about this. So you've got the advantage with a terrestrial network is you know exactly how quickly it's going to roll off. So you just put your base station a certain distance away from the border, and then great, easy. With a satellite, because we've got this beam that's moving, the best way to think about it is if you get a torch and you shine it on the floor, you've got a nice circle. If you then point it out to the side, it becomes this big elongated egg. And so you've got this varying sort of radiation pattern happening constantly. So you've got to predict that accurately and then move the cells or beams accordingly. And then you can actually decrease the power as it goes further down onto the lower elevation angle, so it's not going out into those neighboring countries. And then terrestrial interference, again, same things. So this is where you've got a terrestrial network and then a satellite network. So you've kind of trying to match up between the two. So we don't see this as ever being able to cover an urban environment. It won't have the capacity of a terrestrial network. It's what we're talking here is a cell tower that's got a diameter of 50 kilometers compared to what we have on the ground, which is 1 kilometer. So you're going to have, imagine the same number of people in that area. So you're going to have your terrestrial network, which will cover your cities and your suburban areas. And then when you get to the really remote areas, you'll then move on to satellite. So it's then working out how you can position them so that they don't interfere with each other or have a minimal interference, but you can still get that ubiquitous coverage. And then adjacent channel interference is to do with Doppler shift, which I covered earlier. So this is Blue Walker 3, which is our first main test satellite. So this is to scale. So this satellite will only be 10 meters. And obviously you can't launch something that's 10 meters wide up into space in a rocket. Doesn't fit. So we've got quite a clever sort of system that folds it all down and it fits in this nice compact unit. You put that on the rocket, it goes up and it unfolds. So I saw that the picture was on the other one, but this is, here you go, side by side. This is actually it in the warehouse after being constructed. So this is the test satellite, Blue Walker 3. So the actual satellites will be 5 times the area of this. So give you an idea of scale. I've got just a little animation that kind of should show you how it works. Basically, it will go up in space and it takes a couple of weeks to unfold in space into this big phased array. And then you've got phased array on one side, solar panels on the other side, and then you get your beam forming from that. So that it takes a couple of weeks to actually deploy. Now I'm going to talk about our planned constellation. So as I said, we've got our test satellite going up, which will go up hopefully September. And then we'll have our first phase, which will be an equatorial belt. So we'll have 20 satellites going around the equator, and that will cover plus or minus sort of 8 degrees of above and below the equator. And then we'll have further deployments beyond that, which will go at an inclined orbit, and they'll start to cover parts of Southern Europe and America. And then we'll have further deployments, will fill in all the gaps, and then again, further deployments which increase the inclined orbit, again, covering Northern Europe. So once we get the full constellation, it will be up to 170 satellites. Now, I very much doubt this is going to work. Oh, no. Anyway, it does, apparently. Usually crashes. basically, this is a demonstration of the satellites being launched. So as you see, they start all together in the one rocket, and then they go out and spread out over their plane. And then, so we saw that first one around the equator, and then we saw those next two that kind of start to cover Southern Europe. And then we have further constellations launching again, which will fill in those gaps again. So basically anywhere that's red is currently not being served. The other colors are sort of edge cases. So you will still be served, it's just not as reliable connectivity in those locations. And then finally, it will launch the final constellation, which will cover Northern Europe and Canada and all of South America. So in terms of timelines, we've already launched one test satellite, which is basically what we did is we did the reverse. So we put the ENO-B up in space, the UE up in space and the satellite on the ground to test the link budget, because it's much cheaper to send a tiny satellite up than a massive one. So we did that back in 2019. Then this year, we're going to launch our small scale Blue Walker 3. And then hopefully all of the tests will go well over the next year. And then we'll be able to launch our first constellation at the back end of 2023. And then the subsequent constellations between then and 2025, assuming nothing goes wrong. So thank you very much for listening. Any questions?
I wondered if you had an estimation for the lifetime of the satellite payload.
I think it's 8 years.
Thank you.
Yeah, just a couple of quick questions. The first one, you called this backhaul, but I think it's much closer to front haul that you're describing, correct?
Yes, so I call it backhaul because it's not using the terrestrial frequencies, it's using the QV band frequencies, but it is very much front haul, yes.
Okay, I just a small point of confusion. And
Yeah,
I guess the other is sort of a comment about the reflectivity, and I know that Starlink had all kinds of issues with people on the ground upset with seeing the satellites and being very visible from the ground. And I guess that I don't know what your surface area is compared to Starlink, 100 times or more. You're likely to have to deal with that somehow.
Yeah. So we're going to paint the surface really, really dark black, and it should be basically invisible. The only thing that it will affect is it will block line of sight for stars. So stargazers will be affected as it goes over. But in terms of reflectivity, it shouldn't have any effect because of the material we're covering the phased array in, basically.
Thanks.
So I have two questions. You mentioned that the first shell will have 0-degree inclination. So I wanted to know, curious to know the rationale behind that choice.
So the reason for that is mostly to do with the markets that we want to cover. So this is primarily aimed at African markets, so rural locations, because most of our European countries are pretty well served with terrestrial. I know there's big gaps everywhere, but in terms of actual gaps, Africa has like 90% of its countries not covered, whereas Europe is about 10 to 20%. And that's the main reason for going for the equatorial constellation first. And that's also why we're going for 4G and 5G and potentially even 3G, is because the markets that we're aiming at won't be able to afford 5G phones. You know, half the people in this room probably don't even have 5G phones yet. And they definitely can't afford them. So we want at least to be 4G, and they're begging us to be 3G. So that's the reason.
Do I have time for a second question? Just a very quick one. Sure. So a quick one. So you mentioned that you want to hold back packets at these ground terminals, right? So because it might have some limited buffer size and stuff, do you see packet loss because of that?
It shouldn't make a difference, no. It should. I mean, it should be because it's effectively just going there and then waiting. It shouldn't have any impact on packet loss. In terms of sort of ACAC requests, that's part of what.
Have large buffers.
Yeah.
Can you give us a little more details of how you're dealing with the interference with the terrestrial network? Obviously, you have the handset, you standard mobile handset.
Yeah.
The handset will try to use the terrestrial network and also the satellite network. So how are you dealing with this the interference, and also is there any handover between the satellite and the terrestrial base station?
Yeah, so the idea is that this will be a continuation of the terrestrial network. So whoever does the network planning will have all of their terrestrial base stations and all of those cells and where they cover, and then they'll have their satellite beams in the locations that their terrestrial covered isn't. So they shouldn't be overlapping each other. So they should just be sort of bordering each other, and the only time you'll have interference is at cell edges, which you have on terrestrial networks anyway. Potentially, there is talks of going forward and having sort of using one frequency for satellite and just have a blanket covering. But obviously, that's using up precious spectrum to have a blanket covering.
Okay, thank you.
Is there any other question? Okay, there's a question there at the back.
Cell towers are sometimes shared by multiple vendors. Is there any plans the satellite constellation to also be shared by multiple mobile operators, or is it exclusive to Vodafone?
No, so it will be shared by multiple vendors. So obviously, Vodafone only operates in, I mean, it's a large number of countries, but compared to the whole world, it's a small number of countries. So in all the countries we don't operate, there will be, so AT&T and Rakuten and all the rest of them will have it operating with them. So it should be in every country. The exact logistics of whether or not it will be multiple vendors in an individual country will come down to talks that we have with those countries.
Okay, I think we have time for one short question, if anyone has any. There's one online about what frequency bands will Space Mobile use? Are these bands currently in use for other applications?
So the front haul, as I like to call it, which is from the satellite down to your phone, will use the frequencies that terrestrial networks use. So yes, they are being used everywhere, but they're not being used in rural locations because we don't have networks there. And then the backhaul will use QV band connectivity, which is similar to what Starlink are using, but it's much.
So you might find, so you said that there'll be a set of bands, and as the satellites go over them, the individuals on the ground will not see any difference. But it might be that the satellites themselves will have to switch off and switch on.
Yeah, so basically what will happen is the satellite will turn on and off cells.
Yeah.
So it will determine where we want the terrestrial locations in terms of geographically to be active. Yeah. And then those beams will be turned on, and anything that we don't want to be active will be turned off. So all of the urban locations where you'll have that interference, they'll all just be turned off.
Yeah.
And the border regions as well.
Yeah, that kind of makes sense. Okay. Any last questions? You have 2 more minutes, I guess. If not, let's thank Rowan. And so we're on to the final talk of the day, and you can also see the, just to make the online people a bit jealous. There's some drinks coming here. Change. Okay, so our final speaker is going to be Mark Handley, who has been at UCL since 2003, receiving a Royal Society Wilson Research Merit Award. And from 2003 to 2010, he led the Networks Research Group, which brought the internet outside of the United States, and UCL became the first site to join the ARPANET. And before joining UCL, Mark was at ICSI in Berkeley, where he co-founded the AT&T Center for Internet Research. And he has been very active with internet standards, co-authoring about 33 internet standards documents, including SIP, multipath, and many other things. So over to you, Mark.
Okay, so we were lots of discussion on the chat about routing earlier. I want to talk about routing. I also want to talk about congestion control, traffic management, low latency, high throughput, and lots of buzzwords. So Devapan gave a great introduction to what we're basically trying to do with these LEO satellites. The idea is you can go up to satellite, you can go around on laser links and drop back down again. And there's the potential here to be able to do very wide area, very low latency traffic. Potential, but actually doing it is hard. There's also the potential in these networks to have a lot of throughput, but these laser links aren't that fast. Typically, it looks like something like 20 gigabits is what we can do at the moment. Maybe you can go a bit faster, but it's not going to be a lot faster, and that's quite slow compared to terrestrial fiber. So we've got the potential for low latency, we've got the potential with a lot of satellites for a lot of capacity, but how we use it is going to have to be smart to deliver on that stuff. So what we're looking at is, can we get from pretty much anywhere to pretty much anywhere else at nearly the speed of light in a vacuum? Not in fiber, in a vacuum. This is sort of the current Starlink shells. All the Starlink stuff that you've seen so far really has been on shell 1, which doesn't have any inter-satellite links. This starts to get interesting really as shell 4 deploys, which looks like they will have lasers. So what I'm talking about today is not what you can do on the current Starlink. I'm talking about stuff that you might be able to do on shell 4 or the later constellations with 7,500 satellites in VLEO orbits or even more later on. And so this is still very much an open space for what we might be able to do to manage these networks. Okay, so sort of getting video here. Okay, so this is one of SpaceX's different constellations. It's not the latest one they're deploying. You get the sort of idea of number of satellites in one of these shells. What we're really looking at over this then is using the lasers, as Devapan said earlier, to be able to connect between satellites. And so typically we're looking at something like 4 lasers per satellite, and we can then build out of that a mesh. This looks very similar to the previous one. This is actually the current plans that SpaceX have for Shell 4 in terms of the orbits. And in this particular case, you don't end up connecting to the satellites forward and back along your orbital plane if you want to build a reasonable mesh. You want to connect across. I'm going to use an earlier version of the constellation for these initial animations. It doesn't actually change the purpose of what I'm trying to talk about here, which is actually how we use these networks. Okay, so if you're going to get wide area, low latency traffic, we're going to have to route across these networks. I made a good case earlier for not wanting to do exactly the grid-like thing I'm doing here. You probably might want to go a few satellites. We've done different tiling things that actually work pretty well as well. But again, this doesn't greatly change the message here that you're going to have to go across quite a few satellites. And so the other thing that it really helps you trying to get low latency is not to just go to any old satellite overhead, but try and go in the direction that you're going. And that means that you might have to think now about not just routing across the satellite network, but also routing the RF links
along with the path across a satellite network, and that pushes you into really interesting routing scaling problems. The further you go, the more satellites you're going to have to traverse. But if you look at these kind of constellations with, this is 53.3 degree inclination orbits, they tend to concentrate a lot of traffic along this boundary here, because that's just the nature of where the orbits are. Now you think about what's happening. This is going from London to San Francisco. We're getting quite nice potential latency across this path. This is speed of light latencies, but also all the Europe to US stuff will come around that same band. So you're going to end up with places in these networks where the traffic concentrates. And so this is not just a routing problem. This is a traffic engineering problem, but you're trying to do it at timescales nobody has ever done traffic engineering before. And so that's going to make this a really interesting research problem. Now, the other thing is that actually, because these links aren't that fast, not only do we get to concentrate traffic, we're going to have to spread the traffic across multiple paths. And so this is going between London and New York, showing the 5 best paths. And actually, if you look at the paths you can get, these are two completely disjoint paths. Even going out to the 5th best path, actually the latencies are pretty good. So we have the potential here for doing multipath across these networks and getting good latency, even out to sort of 7th, 8th best path. So if we're smart about how we route traffic across these networks, we can get low latency, even though actually we would naturally concentrate a lot of traffic along these boundaries here. But now we're not just doing a routing problem. This is not a pre-computed routing solution. You've got to do this live because you don't know how much traffic you've got. And so this question of how do you scale this stuff? Well, we just pre-compute the route. Forget it. Isn't going to work if you want to put a lot of traffic onto these intersatellite links. It's fine if you want to run them at low latency, but you're spending a lot of money to put these satellites up there. You probably want to actually route a lot of traffic across them too. So this is the problem I'm trying to solve, is how do we do routing, traffic engineering across these dense networks that have a natural tendency to concentrate traffic inadvertently into hotspots. And so we're going to have to spread the traffic out to avoid the hotspots. We don't know what the demand is in advance. I mean, maybe you just want to sell fixed bitrate pipes, but I suspect that's actually not a great market to be in. You probably want to be able to cope with variable traffic demands. And so we've got to do this live as well. This, I think, is probably the hardest problem in conventional networking at the moment. I don't think anybody totally knows how to solve this. I can't claim I totally know how to solve it, but I'm going to suggest some directions at least. Okay, so what would you want to do? Ideally, you'd want to do some form of load-dependent routing. Except distributed load-dependent routing is really the holy grail of the internet. It's something that was tried back in the 70s and nobody's ever been able to make it work. Generally speaking, if you try to do a distributed load-dependent routing algorithm, you're going to end up with instabilities, and nobody has actually solved them. So that's what we'd like to do, but it isn't going to work. So what else can we do? Well, what we do in the terrestrial networks is we do traffic engineering. And all large terrestrial networks perform traffic engineering. If the only reason you don't need to do it is if your network looks like a tree. But if your network has lots of redundant paths, and pretty much all of them do, you want to do traffic engineering. You want to measure the load on decent length timescales and calculate paths to spread the load across the network. And we know how to do that. We've got techniques like MPLST that work very well. And having this layer between layer 2 and layer 3, where you actually are placing traffic onto paths rather than tweaking link rates in OSPF and so forth, is much easier as a way of actually placing traffic onto a network and spreading it out. So that's really the main way traffic engineering is done in terrestrial networks. But the key points of this is that it operates on slow timescales. And the goal here is to reduce persistent congestion when the traffic patterns are predictable on a day-to-day type timescale. Whereas what we're trying to do in something like Starlink with all these intersatellite links is to do this on a time scale of seconds and on a scale that nobody's done before. So that's what we'd like to do, but the traditional stuff doesn't work for that. And there's pretty much no way you can just put this on steroids and make it work. So we're gonna have to do something different. So what does work beyond that? Well, centralized load-dependent routing does work. And so this has been the sort of the big trend of the last decade or so. You have a central software-defined network controller. You run your network using some form of open-flow switches or something like that. And if you know the traffic demands, you get all the traffic lines into the network, you crunch a placement of the traffic on the network, and you tell the routers what to do. And this actually works pretty well. Google have been running this on their backbone network B4 for a decade now. And so their algorithm that they use does kind of a greedy placement of traffic onto links. You have to know the demand in advance to be able to do the placement. But Google know that because the traffic comes from Google's data centers to Google's data centers, and they tell the data center when to send traffic, so they can know that in advance. There were some slight disadvantages to their packing algorithm with this greedy algorithm that they use. So for example, if we've got trying to place traffic onto this network, what B4 will do is it will fill in the lowest latency paths first for all of its flow groups, and then when it fills those in, it will spread over additional paths as it adds sort of more and more paths to its multipath group. Unfortunately, if you do this, actually, if these delays are high, you can trap yourself into a higher latency solution than you would like. But it's pretty good, and most of the time it works okay. Ideally, you'd do this kind of placement rather than that placement. Okay, so that's one price for the greedy algorithm that those guys run. The other possibility is it is actually possible to lock yourself out of capacity in your network by using a greedy algorithm like this. If you've got this particular set of latencies, it's possible when you allocate traffic to allocate these ones initially together. And now actually you can't allocate the remaining capacity, whereas actually you would have wanted the one on the right, which does this. But because you allocate the lowest latency paths first in B4, you can lock yourself out of that. These are potential downsides to the sort of greedy algorithm that Google used, but it has the big advantage of being fairly fast. And they're running this stuff, at least they were running this stuff a decade ago, on average every 30 seconds throughout the day to re-engineer their network. They're probably running it faster these days, but I don't have stats for that. Okay, so that's one way of doing it. There's another bit of work that my PhD student, Nicola Groziev, did in SIGCOMM 2018, actually, not 20, which is we looked at trying to do this for terrestrial ISPs, where you don't know the traffic demand in advance, you don't directly control it. And actually what we do is we measure the stuff, we try to figure out how things might stat mux. And then we actually feed this into a linear program and actually calculate an optimal placement given the uncertainty we have. You have to do basically an iterative solution by looking at potential paths you might put the traffic on, and you grow the set of paths. So this is kind of cool. It gives you an optimal placement. But one of the things we discovered when we were doing this work was the meshier your networks, the more potential low delay paths you cut, the more likely your network was to actually inadvertently create these traffic concentration hotspots. And so one of the things we looked at in this work was actually not just how to actually route this stuff, but really how do you, and what do these networks do to your traffic? And the worst networks for this tend to look like these meshy satellite networks. You're going to end up creating inadvertent hotspots, and you're going to have to work around them. Now, can we actually deploy these things? Well, actually, neither B4 nor LDR really was designed to work at the scales that we have to work here. B4 probably could work if you were just trying to route the satellite links alone. Maybe marginal. LDR needs about 10 seconds to do a computation, and the best path for these networks tend to change every 10 seconds, so you're not really going to be able to run that. But ideally, you'd like to avoid these kind of doglegs, which means ideally you would like to be able to route the RF links along with the lasers, and that means that your routing computation is not a computation over the satellites, it's a computation of the satellites plus all the terminals. And that's a serious scaling problem. So it's unlikely that we can actually run any of these kind of centralized computations over that kind of network and make it work. Now, what else? If you actually think about this, there's not just a question of how do we place stuff, but as the conversation moves across the ground stations and across the traffic, we've got some really interesting short-term coordination problems. Now, if we're trying to build a low latency network, our goal is not only to not create persistent congestion, it's not to create even transient congestion. And so we've got to be very careful then if we're running these links at reasonably high capacity. Suppose we've got a couple of links that are running, let's say, 75% capacity, and the network is moving across. So as the network moves over, now we want this traffic to go that way, and that traffic link is already full. So we've got to coordinate exactly how we do that shift. And we'd have to do this repeatedly every 10 seconds or so as things move across. So it's not just, you've got to actually factor in the latency of the traffic as it's flowing across your network to exactly when do things transition. So we want this traffic to hit there just as that one starts to depart from there. This is actually quite an interesting coordination problem if you want to route stuff in large chunks. So that kind of coordination of changes, so we don't build even transient queues to mess up our latency, is going to be difficult. It's especially difficult when you try and do a centralized algorithm to do this. On the other hand, if what we do is instead of moving all this traffic from here to there, we slowly start to take traffic off of one path and move it onto another path over the course of maybe a second or so, it starts to become a problem where we don't care so much about doing it exactly the right time. We can actually just use the fact that we're using multiple paths and start to skew traffic across. Maybe we can make it work that way. Okay, so let's stop there just thinking about the routing problem. There is another way to think about this problem. This is a different piece of work that I worked on, which is multipath congestion control, specifically multipath TCP. Multipath TCP is deployed on all your iPhones and Macs and is now shipping in the Linux kernel. And so multipath TCP primarily intended to work in mobile networks where you've got a mobile client, it's moving across your network, and it may, for example, pick up another Wi-Fi base station, and now it can be taking your TCP connection and spreading it across more than one path simultaneously as you move, and different links can come up and down. And so the good thing about multipath TCP is it lets us take our traffic and spread it across multiple paths and gain the advantage of all those different paths at the same time. Now, if you know anything about multipath TCP, you'll know that one of the nice things about it is that it links the congestion control algorithms on different paths. And so if it finds a path that's particularly congested, it will be less aggressive in trying to use traffic on that path, and to be more aggressive on the other path, and actively move traffic from the more congested parts of the network to the less congested parts of the network. This is built into the congestion control algorithm that we designed for multipath TCP. Now, it turns out that actually you can use this to load balance the whole network. So what I'm showing on the right is if these are sort of non-linked congestion control algorithms, and we change the congestion on that top path, then these separate TCP flows going from left to right here, the only thing that's affected is the one that actually goes through the particular link. But if we run multipath TCP on these, so now this is two subflows from the same multipath TCP, it squeezes here, this one increases, decreases, and that causes the next one to respond and so forth. And so there was a bunch of work done by Frank Kelly, Don Tousley, and so forth that we based multipath TCP on, which observed that if the end systems use multiple paths, and enough of them use multiple paths, and they all do this kind of internal load balancing between the more congestion paths and less congestion, you can load balance the whole network just from the end systems without actually having the routing system get involved in doing load dependent routing at all. So this is a really interesting idea. Maybe we can apply this in these networks. So what do you think? Well, OpenTCP has its limitations here. We never really designed it for producing this kind of very low latency, very responsive service. It uses a modified variant of TCP congestion because it has to coexist with regular TCPs in the regular network. And so it needs, as a signal for its congestion control, either packet loss or ECN marks. And if you're trying to build a new fancy layer 2+ in a network like Starlink, we don't want to be creating packet loss or ECN marks due to queues building in order to be a congestion signal. So it's got the wrong congestion signals, but the right concept. It's also, because of its congestion control algorithm, it's just too slow to respond for what we would like in these kind of networks. And it hasn't really got any real built-in ability to prioritize low latency solutions. It only really cares about sharing capacity. But the concept is one that we can actually try and use, but we're going to need a better way of actually placing traffic into the network. So we're going to need much more precise control of where the traffic goes. Now, a long time back, I co-supervised Dina Katabi's PhD, and that was on an algorithm called XCP. And so what XCP does is it has the senders put their round trip time and their demand into the packets, and the packets go through the network. And if they get to a router that's a bit congested, it can reduce the demand signal. And then once it gets to the receiver, you feed that back around and tell the sender what it can do next time. Now, it does this in a way which doesn't keep any per flow state. There's a controller in there that allocates utilization, fills the links up, and then it reshares capacity between the links. And so what the routers can do is then use these bits to predict the load. They use that to control the utilization, and they do some ability to share traffic across. And the great thing about XCP is that it can do this without building any significant queues, and it can change the amount of traffic that's going through the network very quickly, because you're saying what you need, and it tells you exactly what you can have. And if that goes down, it can ramp you down very fast, or it can pull things up very fast as well. So XCP is a great solution that totally failed to deploy in the internet. And it totally failed to deploy because you need to upgrade every router in the internet for this to work, and that really wasn't a good start. But actually, if you're talking about deploying this in a mega constellation, we just have to upgrade every satellite to know about this stuff. And as they're all designed by one company in any particular constellation, that starts to be feasible. So this is sort of graphs of XCP's performance. You can see that if we bring in new flows, it ramps up very fast. It immediately goes to a fair share. There's no real transience when new stuff comes and goes. And this is with a queue size of maybe 4 packets. So you can actually, in principle, have congestion control algorithms if you involve the routers that have the properties we need. We can move traffic from one path to another path within a second, which is what you really need. If your routes are going to change every 10 seconds, we need to move traffic down on that path, now on that path within a second, and then we're done, and then we do it 10 seconds later, we do the same thing again. So the timescales are about right. So can we do a child of XCP and MPTCP and come up with something that we can chuck across these networks that can work edge to edge from one terminal to another terminal, not end-to-end across the internet, but just edge to edge, which allocates the traffic, but allocates it then across multiple paths in these networks? And the answer is, I think we can, but I don't yet have the results to prove it. So the general concept with multipath XCP would be you would request the capacity on the lowest latency path. Everybody knows the map, because that's easy. The satellites are very predictable where they're going to be. You know where you want to get to at the other side of the network. So the routing problem is a source routing problem, not a satellite routing problem. And what we need to do is then request capacity on the lowest latency path across the network. If the traffic doesn't fit, then we need to request capacity on additional paths across the network. And so we keep doing that, and we keep spreading traffic out across more and more slightly more suboptimal paths until the traffic fits. If it won't fit then nothing's going to make this work, because there's too much capacity for the whole network. But hopefully you don't get too far off the best path. Okay, so there's some difficulties here. It's not trivial to extend XCP to multipath. We thought it would be easy. It's turned out it's not been that easy, but we think we've kind of got a handle on it now. One problem is how much capacity do you ask for on each path? Another problem is how many paths should you try? And which should they be? Should they be disjoint, or can they partially overlap? If there's only congestion at one point along the path, then you want to try routes which are not completely disjoint, but just avoid the hotspot. So lots of questions here. So for example, if I'm going to request capacity and I need X, well, I could request X on all of my paths. And yeah, that's great. On the lowest latency path, we didn't get everything we asked for, but we got some. On the other path, we got all what we asked for. Oh, that's great. Now we're allowed actually X plus Y. We've asked for more than we needed. We've reserved more than we needed. You're going to run the low utilization than you would like. So that's probably not ideal. So what else could you do? You could do this initially, but then subsequently only ask for what you think you're going to be able to get. So we discovered that we've got Y. We can subsequently ask for Y on the best path and X minus Y on the other path. And in total, we've asked for X, which is good. But now if what we got on the best path decreases suddenly and surprises us, we actually don't get enough capacity. We only get X minus 1 because that's just the nature of the game. It's unpredictable because we don't know how many other people are doing stuff. And so now the problem is we build a queue at the sender. And although we might be okay with building a transient queue just at the sender, building them in satellites is really bad, but building the sending terminal is, you know, it's going to happen sometime. But we don't want to build a persistent queue at the sender ever. So the difficulty in this space is exactly how much extra capacity to ask for. You're going to have to ask for some. And so there's going to be a sweet spot due to the variability of the throughput as to exactly how much extra to ask for. It'll be some, but it won't be asking for everything on all the paths. And it gets a bit more complicated when you're not just talking about 2 paths, but you're talking about 4 or 5 or 6 paths. Because then you can really ask for a lot more capacity than you're going to use, and that would be a bad idea. So there's a bunch of sort of devil in the detail problems here. There's also an issue if we're only asking for what we thought we could get on there, and actually suddenly the other traffic goes away, we could get more on the low latency path, and we don't know it. So you actually have to modify this to build in some probes to say, not only, I would like this, but if I ask for more, what would I get? And then you can actually solve this problem as well. It turns out the protocol turns out to be quite a bit different from XCP, but it's a nice concept. Okay, so that's that part. Now, the other question is, how many paths did we try? Because we've got to spread traffic across enough paths to not cause congestion. XCP is not going to let us build any queues, but it simply won't let our traffic into the network if we don't ask on enough paths. And that would be bad too. So you need some idea of how many paths to try as traffic increases. And that's going to depend on the other traffic in the network. You know, often one path might be enough, but if it's going across one of those hotspots, it won't be anywhere near enough. Interestingly, though, there's only something like 6,000 inter-satellite links in Starlink phase 4. It's dead easy to distribute the link loads to everybody, all the terminals, all the time. It's just a flooding algorithm. It's trivial to distribute that amount of data. So we can just tell every terminal where the traffic is in the network once a second, or probably once every 100 milliseconds. It wouldn't be a problem. So we can actually have the terminals know where the traffic is in the network, which means that they want to go across a path from here to there, and they look and say, oh, I got this much traffic, that path unloaded, I only need 1 path. Or, uh-oh, it's the rush hour. Need to spread across 10 paths or something like that. You can get a pretty good idea of how far you have to spread the traffic by looking at which paths are currently running hot and which one, how far do you have to spread before you get to the ones that are running cold enough. So I think you can solve this problem too, as to how many paths you try to spread the traffic across, just by having essentially a broadcast mechanism. Okay, so that's sort of the general idea here of how I think you do this. You essentially have the terminals source route their traffic. You source route it across between 1 and many paths. You distribute information to them from the network to say where the congestion is. And you run a control loop that the satellites are actively involved in to tell you when you can increase and when you have to decrease your capacity to avoid building queues within the satellite network. So I think it's possible. I think we can do this. I think we can do active load-dependent routing on timescales of a second or less across a network of millions of terminals and thousands of satellites and actually make it work. It's an interesting possibility. I have yet to prove it, though. So anyway, good mad talk to end the day on.
A couple of minutes for questions. I'll start with one that was there online. Do you feel there's no role for fair queuing or active queue management in these kind of 5G satellite Wi-Fi type of networks?
Okay, it's a good question. The place for something like fair queuing may well be in the sending terminal, right? or something like that to make sure that the different connections that are trying to go across there don't fight each other too badly. But in the satellites themselves, my goal of this is to not have a queue. Yeah, I want the satellites to never have any significant queue. You can't get rid of no queues because you've got incoming laser links and you can have packets coming in from 3 laser links wanting to go out down 1. But so you have to be able to have transient queues of a few packets, less than 10.
Yeah.
But not more than that. And you know, 10 packets of queuing is negligible at 20 gigabits per second.
Yeah.
But if you're using the queues themselves to mediate the traffic between flows, you've already lost.
Right. Okay. Yeah. So you want low latency.
Yeah.
Hey.
Thank you. You mentioned that the inter-satellite links are technically constrained to around 20 gigabits per second. Why is that? Which portion of the design limits it?
So I'm not a laser expert, but I've talked to people who are, and they say, I mean, I talked to a bunch of people who were doing that stuff a couple of years back, and they said they could fairly easily see how to do 10 gigs. This was 2 years ago. They could see a path to 100, but they weren't sure how to get there, but they couldn't really see if they would get much beyond that. And I don't know whether anybody here is expert on lasers, wants to comment on this. I suspect it's just things like signal to noise ratio. I mean, essentially these laser links are telescopes. Yeah. You've got a laser and a telescope. You point a telescope, you've got to track well, but there's only so much energy. If you put out more power, you could probably get more capacity, but then you have difficulty cooling it, and cooling stuff in space is hard too. And you're limited to being solar powered. So there's a whole bunch of trade-offs there. And it seems like the commercial stuff that's available now is in the 10 to 20 gigs range, compared to bundles of 400 gig in fiber. The aggregate capacity across Starlink is going to be quite high. You've got a lot of parallel paths, if only you can use them. But you've got to, if you're going to try and maintain low latency and high throughput and do both at the same time, you've got to multipath. You've got to multipath depending on where the other traffic is. And that's where things get to be a really interesting networking research problem at the moment.
So Mark, my question is, can we use the packet spraying technique in a region part of the topology in this scenario, rather than using multipath TCP, which we might have some problem in the short flow, typical problem?
So the problem, so packet spraying is a technique that's often used in data centers. We've done a lot of work on it ourselves in different contexts. And in a data center where you've got a cluster topology, there's a fixed set of paths. And the optimal thing in a cluster topology is pretty much always spray evenly across all the paths. If there's a failure, yeah, you have to handle those sort of things. But in general, you want to spray across all the paths. Now, in a network like Starlink, firstly, the paths are not the same length. There is definitely a shortest path, and everything else is worse. So you want to, as far as possible, put your traffic on the shortest path. The second thing is the number of potential paths is really high, because you can loop around the world 15 times and then get there, or stuff like that. I mean, and also, even if you've got paths that are vaguely similar, you've got sort of 2 orbital planes, and you know you're going to have to hop between at one point. There's still a lot of paths. So you're not going to spray across all the possible paths. So at what point do you restrict it down to some same set? Generally, you want to pull the traffic back to as close to the shortest path as possible if the traffic will fit. And so even if you weren't running something like multipath XCP, you're going to have to do some load-dependent mechanism to figure out how far to spread. And ideally, you're not spreading across completely disjoint paths, because the hotspot won't be across the whole path. It'll be at some point along it where the traffic from, I don't know, Frankfurt to San Francisco crosses the London to New York traffic or something like that. So ideally, you know something about where the traffic is, and you place it on paths to try and produce paths which are disjoint with respect to the congestion, but not totally disjoint, because then they're higher latency paths than they need to be. So I think spraying, blind packet spraying, you could probably make it work better than not doing anything, but I think you want to be a bit smarter. Yeah, that's just my gut feeling here. I've yet to build this thing.
Mark,
Yes.
a quick question. You mentioned the fact that the uplinks and downlinks should be included in the path calculation, and that, of course, that's also included in the source route. But the uplink and downlink are probably on demand as opposed to sort of permanently available, continuously up. So isn't that a little bit of a chicken and an egg problem? How do you get those? How do you get a link to come up that isn't actually currently up?
So my understanding of Starlink is there's frequencies that are reserved for signaling to bring links up, and so there's already stuff built in there to bring links up when you need to do it. Whether they provide the capability to bring links up to a particular satellite, a particular direction on demand, I would doubt, because I don't think they really have the requirement at the moment. But I don't really see a reason why it can't be done.
Yeah. So it's yeah, it's almost at the packet, or at least at the beginning of the flow. You'd have to have an end-to-end source route that at least creates the up and down link where you want.
Yeah, I mean, you got to talk obviously to the site. If you're the sender, you got to talk to the satellite you want to talk to say, I'd like to set up a session with you, please. So there's going to be some latency in that session setup, and then if you get to the other end, you've got to set up the other end down again. And so the other end is probably the harder part. The first hop is probably pretty easy. The last hop, there's some questions about what you want to do. You might want to set up a slightly, maybe have a default downlink for a satellite and then optimize it after you've brought it up. There seems to be a bunch of possibility of what you could do, but I don't know what the best way to do it is.
I guess my general point is that it involves the physical layer control, as it would, that normally normally the routing would not be required to do that.
Yeah, I mean, you can, all of this stuff would still work if you didn't directly choose which satellite you want to go to first and which satellite you want to be the last.
Just not as good.
It's just, you do pay a latency price for it.
Yes.
And so the question I was trying to answer is, what's the best you could possibly do? And that does involve doing the RF links as well as the lasers.
Yeah. Yeah.
Okay, we're overrunning a little bit, but let's give space for one last question.
Standing between people and their beer.
Thanks, Mark, for the interesting talk. Well, one quick question, when you set up the link from A to B, to set up this link, you must have a knowledge, this is the path. Are you use the standard routing protocol type of the collaboration between this satellite, or you simply centralize and calculate the path?
No, you need, my proposal is that the traffic is source routed. So a terminal that wants to send something across the network has a map of the constellation. It knows where the satellites are going to be at least days in advance, not weeks in advance because of, orbits are not that predictable. But certainly long enough in advance that it can run a map, and it can basically just run Dijkstra and then eliminate path and run Dijkstra again. It's really cheap. I mean, I've run Dijkstra on my laptop for many paths from many sources, many destinations simultaneously. And you can make this work fast enough, easily on my laptop. There's no reason why a terminal can't do something similar. What you can't do is route all of the paths across the network. From a particular terminal's point of view, running the routing computation for itself is easy. But from a central controller's point of view, doing it for 1 million terminals, that's not going to fly. So that's where the central control one makes it really hard. But the fact that each of the 1 million terminals can actually do its own computation actually makes it a comparatively easy problem.
Yeah, and one other thing that you didn't mention, which is wonderful, is that you don't have the state of all of the terminals stored in every single satellite.
Absolutely, don't need it.
Okay, well, on that note, let's thank Mark, and 4 o'clock UK time tomorrow on the same Zoom link. There'll probably be a new YouTube stream, but I will let you guys know via email for that. So take care and see you tomorrow. And for the people here, there's actual drinks there. People online, get yourself a beer or your favorite non-alcoholic drink. And see you tomorrow.